In my last video, I went over what started and ended the 5 ice ages. Briefly, at the end, I mentioned how one of these ice ages is still going on to this day and has been for the whole of human history. What I didn't get to talk about was just how different our world was beneath the ice. The planet's climate had changed, and with it, its geography. Quite simply, the world we're familiar with today was not the same world humans knew thousands of years ago. So today, I'd like to explore this frozen Earth and uncover some of the lost geography from the earliest days of human history. First off, modern humans have been around for roughly 200,000 years, meaning we've witnessed 2 severe glaciations as a species together, between them fitting the Eemian Interglacial, where conditions were more or less similar to what they are today. From this, what we can see is that the climate has been in constant flux for our entire evolutionary history, making it impossible for me to make just a single map to represent it all. So instead, I'll be using this period around 25 to 20,000 years ago as an anchor point, but may diverge a couple thousand years here and there. At this time, around 8% of the planet's surface and 25% of its land was buried beneath ice sheets. For some comparison, only about 3% of the planet's surface and less than 11% of the land is underneath ice today. This difference equates to an additional 56 million cubic kilometers of ice on the planet, which ultimately comes from the ocean. What I'm trying to say is that during this time, the sea levels fell by over 130 meters below current levels, revealing far more land area across the surface of the Earth than we're familiar with today. First and foremost, however, we need to address the glaciers. Obviously, they were all much larger than they are today, but not all ice sheets were created equal. Antarctica froze over 41 million years ago, and for all of that time has maintained ice cover, even while the North Pole remained ice-free. The explanation for this is simple. It's much easier for ice to form on land than it is for it to form over water. What this means is that while the continent of Antarctica itself has stayed icy for far longer than any other place on Earth, the waters surrounding the land essentially act as a barrier for any ice trying to expand beyond this point, and therefore the Antarctic ice sheets didn't actually see all that much growth. Where there were other lands to be found in the south, like the southern tip of the Americas, the Patagonian ice sheet reached far into the Andes Mountains, spanning all the way into modern-day Peru, showing just how vital dry land is for ice to form. Besides this, however, only smaller ice sheets were to be found in the southern hemisphere, in places like Tasmania and New Zealand. The northern hemisphere, on the other hand, is where we'll find most of the Earth's land area, which means that's also where we'll find the majority of the new ice. Before even going all the way north, the third largest ice sheet on the planet back then and today can be found over the Himalayas and Tibetan Plateau, forming at this time an island of ice surrounded entirely by cold desert. Besides this, the Laurentide ice sheet extended over most of Canada, with glaciers making it as far as the northeastern United States. Strangely enough, what remained of what's now the US is one of the only places on Earth to have received more rainfall at this time than it does now, causing several of the basins here to fill with excess water. The biggest of which was the Great Salt Lake Basin, which expanded into what's known as Lake Bonneville. Not too far away, the Pyramid Lake Basin filled in as well to become Lake Lahontan. Besides these, numerous smaller lakes increased in volume here as well. But the greatest lake in North America came about as the glaciers began to retreat. Here, meltwaters pooled against the ice, forming Lake Agassiz. The further the ice retreated, the greater this lake became until it had grown big enough to connect with the nearby Lake Ojibwe. As glaciers continued to move, the lake followed until the ice wasn't enough to contain it all, and eventually the lake drained into the ocean some 8,000 years ago. Today, only the deepest remnants of this once ginormous lake remain, such as Lake Winnipeg, Cedar Lake, Lake Winnipegosis, Lake Manitoba, and the Lake of the Woods. Besides North America, another important ice sheet formed over Europe, spreading from the British Isles all the way into Siberia. Depending on sea levels and the state of plate tectonics, the Strait of Gibraltar would periodically open and close, cutting off the Mediterranean from the Atlantic Ocean. Without the influx of water from the ocean, sea levels within dropped, exposing even more land and leading to a breakup of the sea into a series of lakes. The effects of this sea level drop reached as far as the Black Sea, cutting it off entirely from the Mediterranean, leading to a substantial reduction in size here as well. This, however, is where things kind of reverse. Instead of being cut off from the ocean, the bodies of water further inland, like the Caspian and Aral Sea, actually had a new source of water. Each summer, the glacial meltwaters would flood nearly all of the drainage basins here, causing the lakes to expand far beyond their modern banks. When the ice advanced far enough, it could block the Ob and Yenisei rivers, both of which normally discharge into the Arctic Ocean. Cut off from their typical outlets, the water from these and other rivers would also periodically pool, forming in the process the West Siberian lake system. At its greatest extent some 50,000 years ago, this lake reached over 880,000 square kilometers, more than twice the size of the Caspian today. This form of glacial-bounded lake likely would have been common wherever ice overstepped onto land, meaning what I've touched on is likely only a small fraction of the many lakes that could have arisen during times like these. The last major glacier system we'll talk about formed around the Alps, becoming a smaller glacial island entirely surrounded by land. This is worth mentioning because the whole concept of an ice age came about as a result of observations made by scientists visiting the Alps. It was here that they first observed the deposition of large glacial boulders far beyond where modern glaciers sat, and came to the conclusion that there must have been a time in the Earth's past when the glaciers extended much further than they do currently. If we look further east, we can see the Eurasian ice sheet actually tapers off somewhere in the far reaches of Siberia, leaving most of what's now Russia's Far East surprisingly free of ice. Now, the initial assumption here would be that temperatures weren't low enough to sustain continual ice growth. But if you know anything about this part of the world, you'll know that it is actually one of the coldest regions on Earth. Switching our map real quick over to average annual temperatures, we can actually see this region is clearly colder than both Northern Europe and North America. What this means is that it doesn't really make sense that glaciers did not form here. That is, until we look at the land itself. With less water in the ocean, the entire Siberian shelf sat above sea level, filling in much of the nearby Arctic Ocean to the north and pushing coastlines further east as well. By further distancing these lands from sources of water, i.e. the ocean, this region became extremely difficult for moisture to reach. This, compounded with the air's reduced ability to hold water, and together means the deep interior of Asia just never received enough snow to begin building up ice season after season. To make matters even less favorable, wind patterns at this latitude blow air towards the northeast, pushing dry continental air out over moist ocean air. Meanwhile, over here, the exact opposite occurs, where moist ocean water was pushed over the land, which explains why we see ice forming off the west coast of North America, but not Russia's Far East. This is important because the lack of ice combined with lower sea levels led to the formation of a land bridge between North America and Asia, what's now known as Beringia. It was this land bridge that early human explorers crossed to begin populating the Americas, meaning we have this land bridge to thank for an entire chapter of human history. This, of course, wasn't the only land revealed by lowered sea levels. Further down the coast, we can see the shallow seas surrounding Japan were dry at this time too, connecting the islands to the mainland. When sea levels reached their absolute minimum, the lower parts of the Japanese peninsula would connect with Korea to create yet another massive lake in the interior of Asia. The Yellow Sea, on the other hand, was completely drained at this time, connecting the Korean peninsula not only to Japan but to China as well. And sorry Taiwan, but during this time you too were part of mainland Asia. Even further down the coast, we'll find perhaps the greatest reclaimed lands anywhere on Earth at this time, as the shallow waters dividing the islands of West Indonesia dried up, and a contiguous landmass rose to connect Sumatra, Java, and Borneo to Southeast Asia, forming what's known as the Sunda Lands. At its greatest extent, the Sunda Basin could reach as far as the Philippines, while never pushing further east than the island of Sulawesi. As a result, it's here that an important natural boundary was formed. Being an extension of Eurasia, animals moved freely between Asia and the Sundaland, populating this region with the animals typical to the continent, such as elephants, apes, tigers, rhinos, Eurasian animals. Past this line, however, only animals originating from Australia and New Guinea had access, which is why you'll find things like marsupials and monotremes over here and basically nowhere else, making what's known as the Wallace Line the natural barrier between two entire continents. The last major island to join Asia was that of Sri Lanka, which tacked itself nicely onto India. And it was only 500 years ago that this changed, when a cyclone came through and washed away the last bridge between the two lands. Continuing west, we'll find the Persian Gulf entirely filled in, turning the Arabian Peninsula into, well, not a peninsula. Around the other side of Arabia, we can see that the shallowest part of the Red Sea cut the rest of it off from the Indian Ocean, turning the Red Sea into the Red Lake, while simultaneously connecting Asia to Africa in two places instead of just one. Africa on the whole, however, was perhaps the least changed of all the Earth's landmasses, gaining a little ground here and there, but nothing huge, especially when compared to Asia. So moving on to Europe, if it wasn't under a tremendous sheet of ice, you'd be able to see that ocean levels dropped far enough to drain the Celtic, North, and Baltic seas, exposing the lands of Doggerland and connecting Britain, Ireland, and Scandinavia to the rest of Europe, while even creating a few new islands between expanded Europe and Iceland. Even further north, we can see a huge area of land would have been exposed, filling in the Barents and Kara Seas. Though all this new land really did was make it easier for ice to come in and cover it all up. North America has a very similar story actually, where under the ice, virtually all of the Canadian islands became fully connected to North America again, even going as far as Greenland. Besides these expansions hidden under the ice, however, North and Central America weren't changed all that much. We'll find the most notable differences by looking at the Caribbean actually, where we'll see the Florida Peninsula was about 2 to 3 times bigger than it is now, though all of the islands throughout the Caribbean grew in size as well, with Cuba nearly connecting to the extended Yucatan Peninsula and Nicaragua reaching out to nearly grab Jamaica. The biggest visible change to the American landmass, however, and really the only big change to happen to South America, came with the draining of the Argentine Sea, which added over 1.3 million square kilometers of incredibly flat land to the continent, though to be honest, most of this would have been uninhabitable tundra for the most part. The last big change to the continents comes by looking at Australia and New Guinea. Today, we can see only the thin and shallow Torres Strait separates the landmasses, but I'm sure at this point you can guess what's coming. Lowered sea levels closed this gap and connected the two lands into a single continent, while also managing to absorb the island of Tasmania to the south. This continent, given the name Sahul, would have measured nearly 12 million square kilometers, making it roughly equal in size to modern-day Antarctica. Besides those small glaciers found in Tasmania I mentioned earlier, Sahul would have been the largest ice-free landmass on the planet, and therefore the landscape here was largely unaffected by the Ice Age. Beyond the continents, all of the Earth's islands were also changed considerably by the lowered sea levels, but I can't actually go through every single island because there are just too many. So an honorable mention definitely goes to the islands of New Zealand for, at the very least, trying their very hardest to become a continent. While they did manage to unite themselves into a single island, sea levels never dipped low enough for the entire Zealandia shelf to be exposed. So what the planet was left with was a mega New Zealand, measuring roughly 520,000 square kilometers, making it the second largest island on Earth at the time, as many of the larger islands today weren't exactly islands back then. The title of largest island, if you're curious, would have gone to Madagascar, which, while only around 580,000 square kilometers today, would have reached a size of over 700,000 square kilometers back then. Now, beyond all of the glaciers, lakes, islands, and continental shelves, the surface of the Earth was changed in one last considerable way, and that's in terms of its natural environment, or in other words, its biogeography. This, however, could fill a video of its own, so if you'd like to see how nature reacted to all of these shifting conditions, let me know in the comments. Okay, it's at this point in my videos that I usually ask people to help support me over on Patreon, but considering the worldwide pandemic that's happening right now, it kind of feels wrong to ask people for money while my revenue has largely been unaffected by this. So to everyone who continues to support me, thank you so much. But also please don't hesitate to stop your commitment if this situation has affected you. Other than that, make sure to watch my last video if you haven't already to learn what caused this and other ice ages in the first place. Stay inside, wash your hands, thanks, and goodbye. For over 85% of the Earth's 4.5 billion year history, the planet has maintained a worldwide greenhouse, with hot and humid climates reaching from the equator all the way to the poles. But every so often, the Earth experiences a reversal. World temperatures drop, and glaciers reach out to clasp the Earth in ice. These conditions have been referred to as an ice house Earth, or more commonly, ice ages. But catastrophic changes to the climate don't happen without a reason, so today I wanted to journey back in time to look at some of the causes behind these glaciation events and see what ice ages might be able to teach us about the future of our planet's climate. The Earth has only experienced 5 major ice ages. The first began 2.4 billion years ago when the only life to be found on the planet was ocean-dwelling, unicellular, and anaerobic. This all changed when evolution delivered cyanobacteria, the first organism capable of converting carbon dioxide and water into useful sugars with the help of the sun, photosynthesis. The important difference here, however, was in the waste product generated, gaseous oxygen. Prior to this, the highly reactive gas had never before been found in the atmosphere. Instead, methane, a powerful heat-absorbing greenhouse gas, was found in abundance. The only problem was, in the presence of oxygen, methane reacts to produce carbon dioxide and water vapor. Carbon dioxide, while still a greenhouse gas, isn't nearly as good as methane at retaining heat in the atmosphere, while water vapor mostly would have precipitated out of the air and into the oceans, minimizing its effects on the climate. What this led to was the atmosphere being gradually drained of its methane and replaced by less substantial greenhouse gases, until for the first time ice formed on the surface of the Earth, beginning what's known as the Huronian Ice Age. The extent to which glaciers encompassed the planet during this time is not entirely known, as each subsequent ice age tends to remove nearly all evidence of those preceding it. But we do know that after most of the world had been buried beneath ice for 300 million years, the veil slowly lifted and the Earth transitioned back to a swampy, lush jungle. From here, it was more than 1 billion years before the Earth glazed over with ice once again, this time thought to have been caused by an increase in volcanic activity. Now, considering volcanoes have been, and still are, one of the largest sources of greenhouse gases on our planet, this statement at first might seem backwards. But the other major side effect of volcanism is the creation of new rock on the Earth's surface. And while it's easy to assume that after their formation, these rocks remain mostly fixed and unchanging, this isn't true. Different aspects of the environment are always interacting with one another, either physically or, more importantly to us, chemically. You see, carbon dioxide in the atmosphere can react with water vapor to form carbonic acid. When this weak acid eventually rains down to the surface, it interacts with newly generated rock, like feldspars, leading to what's known as chemical weathering. What this does is alter the feldspar into what's known as kaolinite, while producing calcium and carbonate ions, which, surprise surprise, react to form calcium carbonate, another rock. What this means is that the formation and weathering of new rocks can actually draw carbon dioxide out of the atmosphere and lock it away into new rock. And shortly after, as a result, Earth entered into the most severe glaciation event in history, the Cryogenian Ice Age. Glaciers extended as far as the equator, while the ocean became a mixture of ice sheets and slush, sealing virtually the entire planet beneath a layer of ice. But eventually, either by chance or more likely as a result of the extreme resource limitations of the time, this period saw the evolution of the first predatory zooplankton, which could feast on the virtually defenseless phytoplankton, providing for the first time a control mechanism for these abundant photosynthesizers. So, after 100 million years of sustained volcanism, with oceanic carbon retention at an all-time low, the balance of power shifted back towards greenhouse conditions and the Earth thawed once more. The next ice age wouldn't come for another 200 million years, with what's known as the Andean-Saharan Ice Age. And I have to be honest here, not much is known about this period of glaciation. It's thought to possibly have been the result of a massive collision somewhere in the asteroid belt known as the Ordovician meteor event. What this did was send a large amount of debris into the path of Earth's orbit, which over hundreds of thousands of years would fall to the Earth, increasing the atmospheric dust levels to several orders of magnitude higher than what they are today. And when dust is in the atmosphere, the small particles can sort of act like tiny mirrors, reflecting away sunlight before it can reach the surface, basically the opposite of a greenhouse gas. Whether or not this was the main cause behind the third Ice Age event, we know that only 30 million years were spent under the ice, making this the shortest ice age by far. Not long after this, however, by around 360 million years ago, a new evolutionary path was being explored, which led to another precipitous drop in carbon dioxide and abrupt rise in atmospheric oxygen. For the first time in Earth's history, plants began to grow on land. Before this point, life had essentially been restricted to the oceans, but with the development of things like tree ferns and lycopods, Earth's landmasses were rapidly colonized with carbon dioxide depleting and oxygen producing life. Pretty soon, plants were building structures like lignin and cellulose, which, due to their complex structures, have incredibly slow decomposition rates. This means there was enough time for them to get buried, preventing their further breakdown, and storing the carbon in their bodies beneath the surface into what would eventually become coal. As a result, atmospheric oxygen levels rose to over 35%, while carbon dioxide levels fell below 300 parts per million, and the planet entered the late Paleozoic Ice Age. Ironically, it got so cold that many plants had trouble growing, and oxygen content was so high that fires could burn hotter and larger than they can even now, helping to periodically remove vegetation and return carbon to the atmosphere. On top of this, around 25 million years into this icehouse event, the Earth's many landmasses assembled into a single monolithic continent, Pangaea. With an interior too vast for most moisture to seep in from the oceans, the water that kickstarts chemical weathering wasn't coming in contact with the rocks at the core of the land. As a result of having two major carbon sinks weakened, CO2 could once again begin to build back up in the atmosphere. Just a nudge is all it takes, and from here, as some ice melt began to occur, this revealed the darker surfaces beneath, otherwise known as decreasing the albedo of the planet's surface, leading to greater heat absorption, creating a feedback loop until the Earth was again free from ice. From this point, the Earth had to wait another 200 million years before South America broke apart from Antarctica, opening up the Drake Passage and allowing for the formation of the circumpolar Antarctic Current. What this did was isolate the southern continent from the warmer equatorial currents that otherwise would have been forced to circulate around the pole. Cut off from equatorial heat, Antarctica formed massive ice sheets 41 million years before there would be ice found at the North Pole. But slowly, as the continents continued to break apart, the shoulders of North America and Eurasia closed in around the Arctic Ocean, again blocking those warm equatorial currents from entering the waters here. Meanwhile, the Indian subcontinent was colliding with Asia and as a result was building the Himalayas, or in other words, exposing more rock for the same chemical weathering we talked about earlier, leading to more CO2 leaving the atmosphere and therefore decreasing the world temperatures enough for ice to form at the North Pole, officially marking the start of the Quaternary Ice Age some 2.5 million years ago. Due to the recent timing of this glaciation, this is also the ice age we know by far the most about, and some of the ice created during this glaciation is still on Earth today. By drilling into the ancient ice preserved beneath Antarctica and analyzing the composition of the trapped air bubbles, we've been able to determine historic carbon dioxide levels, dust concentrations, and even reconstruct temperature. Now, looking at this, it's pretty easy to see the correlation between carbon dioxide and temperature, but their correlation with dust might not be as obvious. You see, when the Earth gets colder, the air overall cannot hold as much moisture, and the planet as a whole becomes drier, exposing the surface and allowing for greater amounts of dust to be kicked into the air. So knowing this and going back to this graph, what we can see is that there's a spike in dust particulates every time the Earth's temperature reaches its periodic minimum. But what I really wanted to use this graph to explain was the cycle of colder temperatures followed by relatively warmer ones, all during an overall ice age. These cycles are what's known as glacial interglacial, and it's likely that all previous ice ages experienced similar patterns to these. The cause of this glacial interglacial cycle has to do with the way, or ways, the Earth orbits around the Sun. The Earth's orbit periodically changes in three main ways: precession, obliquity, and eccentricity. Now, correlating any one of these cycles to the glacial interglacial patterns is difficult because they all happen simultaneously, and the effects of one may either cancel out or exaggerate the effects of another. But simply put, we can see that the Earth's relation to the Sun is the source of cyclical changes to the Earth's climate. What this also reveals is that changes in relation to the Sun are not responsible for beginning or ending any of the ice ages. If they were, we'd see ice ages not just behaving, but actually occurring cyclically as well. Each one is truly unique. What we can learn from this is that while smaller variations in the Earth's climate can be caused by changes in the Earth's position relative to the Sun, the larger climatic changes, i.e. the ice ages or global warming events, have and always will be determined by the composition of our atmosphere. Using this graph then, we can see that without humans, the Earth would be on track to re-enter a far colder glacial period sometime in the upcoming 50,000 years. But now showing modern carbon dioxide levels, we can see that what we've been putting back into our atmosphere pales in comparison to anything we've seen previously over the past few 100,000 years. And if we've learned anything at this point, it's that because of the Earth's inherent composition, which was determined billions of years ago during its formation, the planet naturally favors greenhouse conditions. Every time the climate has diverged from this, it was in large part due to the removal of greenhouse gases from the atmosphere. And the only way the Earth could return to such conditions was for these gases to be replenished. Today, we're putting this carbon back into the atmosphere and simultaneously reducing the planet's ability to absorb and sequester it. Given enough time, the Earth will react in a huge way to this change for the warmer, which is a problem not because I don't like warm weather, but because humans evolved during and as a result of the icehouse conditions experienced by the Earth historically. These are the ideal conditions for human life, and while the cycles of global warming and cooling have never fully eradicated life on Earth, they have been responsible for mass extinction events nearly every time. Hey, so I hope you enjoyed, and if you did, well, you're in luck actually, because this was part 1 of a 2-part Ice Age series, and next time we'll be going a bit more in depth about that Ice Age we're in right now, so subscribe and stay tuned. Of course, if you'd like to help me in this process, you can always check out my Patreon like all of these people going by on screen. It's a big help getting these videos done. Thanks. This summer, I'll be heading to Europe for about a month and a half. Don't worry, I'll still be trying to make videos the whole time, but I've never been, and I'm very excited about it. Anyway, when thinking about what clothes and stuff I'll be bringing, I figured I'll just bring my typical summer clothes, as summers in Europe are fairly comparable to those I've experienced my whole life living in New York. The only thing is, that's sort of strange. I mean, if we look at a map of the world, any old map will do, and we lay some lines of latitude on it, we'll have, well, a pretty standard map still. But the assumption made with these latitude lines is that the further away from the equator you get, the colder it gets as well. Makes sense, right? So if we look at the general latitude I live at now, and then follow that line all the way to Europe, we'll find that I live roughly at the same latitudes as central Spain and Italy. Actually very close to the latitude of Madrid, but also close to Barcelona or Rome in Italy. All of which are on average both warmer and drier than New York, despite being at the same or even higher latitudes. To find a place more similar to the climate of New York, maybe a city like London, we'll need to move over 12,000 kilometers north. If we look at London's latitude then and see where that corresponds to in America, we'll find northern Canada, mostly Quebec, which is on average much colder than where I am in New York. Now, if what we said about latitudes is true, and it gets colder the higher you go, which it is, how can it be that Europe on average is much warmer than its American latitudinal counterparts? Well, maybe we should take a look at a map again, except this time let's look at one that shows average temperature across the world. If we look at Europe, we'll see it's mostly this mustard color, which represents an average temperature of about 10 to 12 degrees Celsius. Looking for this same temperature in America, we'll find the same color range from right around Virginia to the bottom of New York. Okay, yes, this is what I was saying before. But if we go back to Europe and then move only latitudinally from Europe west to America, we again find northern Canada, and now we can really see the temperature difference between these two places. Here, the map is mostly the cyan light blue color, which represents an average of around 0 degrees Celsius, pretty cold, and a whole 10 to 12 degrees colder on average than neighboring Europe, despite being at the same exact latitude. So that proves that latitude isn't the only thing that influences climate. But then this still leaves the question, if not latitude, then what causes this difference in climate? To figure this one out, we're going to need to look between Europe and America, at the Atlantic Ocean. Turning the map to ocean temperature mode, if we look back to New York, we'll find this very thin line of greenish blue surrounded by larger zones of different water temperatures. Moving over to Europe though, we can see this greenish blue layer expands greatly and essentially covers all of Western Europe. What this means is that the ocean temperature surrounding most of Europe is on average about the same temperature as the ocean water much further south by New York. If the ocean temperatures are the same in these two places, that explains why they have such similar climates. Man, it's really lucky that I'm from New York, or I would have had no idea how to begin this video. So these warmer ocean temperatures around Europe are the cause of the continent's higher than average temperatures. But that still leaves the question, why are these European waters warmer? To answer this, we're going to need to learn about the Gulf Stream. You see, prevailing winds in the area move from southwest to the northeast. These are called the westerlies, and essentially take air from around the Gulf of Mexico and Caribbean and blows it up towards Western Europe. This creates a very similar ocean current where warm surface water from the Gulf of Mexico and Caribbean move along the coast of America, ending somewhere generally between Iceland and Norway. As this warm water travels up, its heat is dissipated to the surrounding areas, i.e. Europe, making it warmer than it should be. But the title of this video isn't why Europe is warmer than it should be, which means we're only just getting started. You see, this process of water cycling in the Atlantic is part of a larger water circulation system called thermohaline circulation. While winds are pretty good at moving surface water, anything below the surface isn't so easy, so for this ocean circulation to function, other forces need to drive it. That's where the thermohaline comes into play, as the two main movers of deep ocean water are temperature and salinity. Let me explain. Being relatively close to the equator, temperatures around the Gulf of Mexico and the Caribbean are hot nearly year-round. These hot temperatures cause the ocean water here to evaporate much faster than they would further north. As the water evaporates, it leaves the salt in the water behind, and therefore the remaining water becomes highly concentrated in salt. Now, having more salt in your water does two things. First, it makes it taste horrible, and second, it makes the water more dense. This dense water doesn't sink, however, because it's warm, which works to counterbalance the high salinity, making it more or less of regular density here. But as it travels up the American coast towards Europe, as I said, it loses its heat to the surrounding land, itself becoming colder. The colder the water becomes, the more dense it becomes as well. But also, another thing begins to happen here too. Some of this water travels far enough north to become Arctic sea ice. When this happens, the water forms into ice crystals and leaves its salt behind, making the water surrounding the ice even saltier and therefore even more dense. Finally, this cold, extremely salty water is too dense to remain near the surface. Now, the Gulf Stream moves around 100 million cubic meters of water per second, and all that water has to go somewhere. What ends up happening is all that water sinks. The water sinks down about 4 kilometers in what can only be described as the greatest waterfall anywhere on Earth. Well, actually several of the world's greatest waterfalls, as the waters fall in what are called chimneys that can reach 15 kilometers wide. This amounts to each one of these chimneys moving up to 17 million cubic meters of water per second down to the ocean floor, which comes out to about 15 times more water than what's transported by all the rivers in the world combined. This downpouring of water does two things. Near the surface, this falling water creates a maelstrom which pulls in more water from the surroundings. And it also transports water into the deep ocean, where it begins to travel back south, taking as long as 1,500 years to return to the surface. This specific process of sinking water in the North Atlantic is called Atlantic Meridional Overturning Circulation. But because that's a mouthful, I'll just say AMOC from here on out. With both of these things happening, the maelstrom and moving south, the AMOC can be maintained indefinitely, as long as the two conditions necessary to drive the process, temperature and salinity, aren't messed with on a global scale. But oh wait, we are messing with the ocean temperature and salinity on a global scale. So we all know, or at least we all should know, that human activity is causing the atmospheric composition to change, with the end result being the warming of the Earth, which has two effects on this circuit. Well, actually, it has a lot of effects, but we'll be concerned with two. First, warmer air temperatures at higher latitudes means the waters up here become warmer too, and therefore less dense. This means the water in the AMOC doesn't sink as readily in those chimneys. Then the second, and perhaps more important of the two effects, is that warmer temperatures means melting ice. As large amounts of ice from the Arctic Ocean and Greenland melt, that floods surrounding areas with high quantities of fresh water, lowering the overall salinity of the ocean water in this area. With lower salinity, the water is, again, less dense, which means, again, it's less likely to sink. Or basically, the whole system depends on waters here being cold and salty, while climate change is making them warm and, well, there's not really a single word to mean less salty, so I'll just say unsalty. Overall, these two changing conditions should, in theory, weaken the circulation system, with the worst case scenario being a complete shutdown. Now, there is some disagreement within the scientific community as to whether a slowing of the circulation has actually been observed in recent years. Some data from NASA suggested despite global changes in climate, this circulation has actually been speeding up slightly since 1993. Meanwhile, a study published in 2015 reversed this, claiming circulation has slowed down between 15 to 20% over the last 200 years. So there is still some division in the scientific community as to whether this slowdown is happening, though our most recent data suggests that this hypothesis is drifting dangerously close to becoming a theory. And because it's a lot better to think about the future and prepare for potential disasters instead of ignoring all the signs pointing towards them, now we need to ask what would happen if climate change in fact does lead to a slowing down or even a breakdown of this thermohaline circulation. Well, for starters, it would mean no more giant waterfalls, no more warm water flowing north, and no more free utilities for Europe. But perhaps worse than what wouldn't be happening is what would begin to happen. First, the heat produced around the equator would be retained here, making this area warmer than it is now. This could potentially cause greater droughts, more powerful storms, and throwing all sorts of weather systems out of whack. That would mean any agriculture here would be vulnerable to decreased production as local weather patterns shifted, and crop fields could become subject to desertification. The second impact of this would be almost the opposite. Without the system bringing warm water and air up north, the higher latitudes would be allowed to get much colder than they are now. Now, the extent to which both of these changes would occur, and by how many degrees temperature change would actually be expected, is near impossible to predict with current models. So, to get any more specific than this, we'll need to look into Earth's past. Luckily, similar changes in the thermohaline circulation system have been recorded, and samples from ice cores taken in Greenland revealed the entire thermohaline circulation system has shut down before. As the enormous glaciers of the last ice age receded, this released a tremendous amount of fresh water back into the ocean. This had the exact expected results, making the ocean water in the North Atlantic too fresh, and therefore not dense enough to sink, and the whole AMOC shut off. This was followed by a 7 degrees Celsius drop in temperatures around Greenland over the span of just a few decades, which is incredibly fast on a geological timescale. It was only after these meltwaters ceased that the circulation could slowly begin to restart. Even more recently, however, between the years 1300 to 1850 CE, an event known as the Little Ice Age occurred. This was a time when average global temperatures decreased by about 1 degree Celsius. Immediately preceding this event was a period called the Medieval Warm Period, which reached its peak around 1100 CE. This was a time when average global temperatures, and especially those over Europe, were much warmer than previous eras. By around 1200 CE, this warm period came to an end, and the average global temperatures steadily declined until a minimum was reached by around 1600 CE. This pattern of warming, followed by a sudden drop in temperature, can be seen as analogous to our current situation, in which we are throwing the Earth into a period of increased warmth, with the potential for a sudden and more extreme reversal of such a trend. The worrisome part for us is that the heating we've caused to the planet has been to a far greater magnitude than the medieval warming period. And so, if the two events are seen as analogs, this could mean the resulting cold spike from global warming could be far greater in magnitude than that of the Little Ice Age, possibly resulting in a medium ice age or even a large ice age, though probably not an extra large or a double extra large ice age. But the changes would certainly be noticeable over a single human lifespan. Moreover, evidence has been found that this swing from medieval warm to Little Ice Age was in fact related to changes in ocean circulation, showing the Gulf Stream to have weakened during this time of the Little Ice Age. Whether or not one of these was the cause of the other is still up for debate though, and not all data is aligned neatly for a single conclusion. Essentially, studying the past climate is hard, and all sorts of things can cause fluctuations. But that doesn't mean we can't at the very least try to understand the future by looking at the past. All that can really be said at this point is that evidence exists which points towards a possible cooling of the polar regions as global temperatures continue to rise. And the destabilizing of the ocean circulatory system in the past has been associated with ice age events. And if that's the case, our world would become one of, well, fire and ice, where average temperatures around the equator exceed our current levels while those around the poles drop far below what we're accustomed to. Either way, if we can't reverse this trend of circulation breakdown that's been observed for the past 40 years at least, Europe can expect decreased temperatures as less heat is brought up to the continent, and the climate here will likely become more similar to that of northern Canada. Cold, snowy, bad for crops, and overall less pleasant. No offense to any northern Canadians though. While countries in and around the equator could expect higher temperatures, potentially causing droughts and lower crop yields as well. Yeah, happy stuff. Anyway, if you want to keep learning about this, I put a couple links/sources in the description. If you want to help videos like these to be made, well, you might want to check out my Patreon like all these people did, and consider becoming a patron. It really helps this channel out, which, if you think about it, helps you out by giving you more videos. If not though, that's okay, but maybe at the very least, subscribe if you want to keep seeing videos like this. I've really started to dislike making these outros, so let's keep things fast. I'll be back soon with another one. Thanks. Hey, so the creators of YouTube joined together to plant 20 million trees, which is a great cause and you should definitely donate if you can. But today I wanted to look at the impact of something like this, and I'd also like to talk about the best ways to actually go about a project like this. To start, I'd like to talk about forest diversity. While a forest might seem like a single homogeneous entity, they're not. Rather, forests are collections of many different tree species, each one interacting with the environment in different ways. One species may provide the preferred seeds for a bird to eat, while another may grow leaves that are good for the construction of nests, and yet another tree's branches may grow in a way that makes nest building possible. It's generally agreed that a greater diversity of trees produces a greater variety of forest resources, which in turn sustain a greater richness of animals and other life. The greatest example of this would be the Amazon rainforest, where the tree diversity can reach up to over 1,100 different tree species in as little as a quarter of a square kilometer, while up to 16,000 different tree species exist here overall. So it's no surprise that predictions for the total number of animal species in the Amazon go as high as 10 million. That's why the Amazon is also one of the oldest forests in the world, surviving for over 55 million years. To see what happens when biodiversity isn't taken into account, we can look at the biggest reforestation project in history, China's Great Green Wall, a massive reforestation effort starting in the 1970s which continues to this day and plans to finish around 2050. Its purpose was to prevent the advance of the Gobi Desert into the Chinese interior by planting a barrier of trees across northern China. Because the focus was on growth instead of diversity, only a small variety of fast-growing trees like Chinese poplars were planted in most sites, having even been called green deserts. Worse than that, in the year 2000, when Anoplophora infected many of the newly planted artificial forests, a reported 1 billion poplar trees died, setting the entire project back by 20 years, revealing just how vulnerable monocultures can be. Diversity, of course, has its limits as well. You can't simply take different tree species found all over the world and plant them somewhere else, expecting a successful ecosystem to appear. Instead, plants native to the area should be used. Not only does this give them a better chance at surviving whatever unique climate conditions a region might experience, but it also ensures that the trees planted can eventually be used by the animals in the area, which is kind of the point of all this. Assuming that the people behind Team Trees already know this, the next step is asking how we can plant 20 million trees to make the absolute maximum impact. First off, while 20 million trees is a lot of trees, is that actually a lot of trees? Well, in MrBeast's video, he says they're planting them 8 feet apart on either side, giving each tree 64 square feet. If you did the same for every tree planted, that would give you a forest covering 1,280,000,000 square feet. Translating this number into one that actually makes sense, that's nearly 120 square kilometers, which no isn't enough to save the world, but is still a really decent reforestation effort, and is like reforesting all of the Bronx in New York City. Once planted, each tree will begin to take in carbon from the atmosphere, and using it to construct its body and leaves will sequester around a ton of carbon dioxide over the first 40 years of its life. More importantly, if done correctly, the trees will begin facilitating the introduction of additional species from the surroundings. An important thing to note is that many species come to the forest not only for the resources, but also the protection the forest provides from potential predators. Because of this, animals and even plant species will concentrate themselves in the core of the forest, leaving areas of transition around the edges. A result of two different ecosystems overlapping, these transition zones can actually become thriving and diverse ecosystems in their own right. But when planting a tree on land cleared by humans, there isn't really going to be this mixing of environments, so these transition zones are going to be areas of lower productivity. With each tree added though, the ratio of core to periphery grows larger, meaning we maximize the area of highest productivity forest by planting all 20 million trees together. If done perfectly, this would result in a circular forest with a radius of over 6 kilometers, which is pretty good for a standalone forest. However, the Earth, luckily, already has some forests, which means we can actually do better than this. By placing our new forest against a pre-existing forest, we can further decrease the area of transition while increasing the number of trees in the core of the forest. Even better than this, however, if there's a hole inside of a pre-existing forest, then all of the trees planted will contribute to the forest core. Having a clear hole perfectly cut out of a forest might seem like a bizarre circumstance, but things like this aren't really uncommon these days. But with a little creativity, we can do even better. Consider this forest. Let's say it's big enough to support 6 hunting grounds, which is enough to maintain one small population of apex predators, as long as they continually migrate between resources. Okay, but now say a wall, or more commonly a road, is made to cut through this environment, separating one side from the other. Without as many resources to feed on, many members of the pack starve to death, and those that remain aren't numerous enough to continue hunting effectively. In the most extreme case, the apex predator goes extinct in this area. And while some of us might figure the extinction of dangerous predators to be a good thing, this can have tremendously negative impacts on the environment. I actually went out to a forested nature preserve near me where this exact thing is happening. Predators like coyotes and wolves were essentially eradicated from this area, which has led the deer population to explode, eating every sapling tree until the forest floor is completely empty. I took this footage at the height of summer when all the plants were in bloom, but even then you can still see deep into the forest. For a comparison, this is what a healthy forest floor should look like. Plenty of undergrowth, giving the forest a greater level of complexity. But here, the only thing that survives on the floor is grass, which, while it might look cool, can be a sign of impending death, an indicator that the process of becoming a grassland has already begun here. This series of compounding effects on an ecosystem is called a trophic cascade, and once the grass grows high enough here, it'll be able to block out sunlight reaching the very bottom of the forest floor, effectively smothering out slower growing plants like sapling trees. The forest will thin out over time, becoming a woodland and eventually a grassland. In short, even though this hypothetical road damaged very little of the forest directly, all of the forest was or will be, in fact, damaged. But if you left even a small part of these two forest fragments connected, this would open the rest of the hunting grounds back up, effectively creating a single forest again. These connective areas are called corridors, and we've just started to see concepts of them make it into small-scale resource management and new construction projects. Using those 20 million trees to create corridors, habitats containing literally billions of trees could be brought back into the ecosystem. And by using the smaller fragments of forest to guide the planting of corridors, many smaller forest fragments can also be reincorporated while reducing the number of trees needed for each corridor. And this, if you ask me, is the best use of 20 million trees. Okay, so now that we have figured this all out, the last thing I want to ask is what type of forest should we try to replant? The answer to this obviously depends on funding and project goals and logistics, but generally, if you're just trying to reforest the earth and you want to support the greatest amount of biodiversity, then rainforests are your best bet. All rainforests are important, but the ones I'd suggest prioritizing are the ones that are really hurting right now, like the Southeast Asian rainforest, once bigger than the Amazon, though today it's mostly fractured by the cities and farms of around 650 million people. Another incredibly damaged rainforest is the often forgotten sister to the Amazon, the Atlantic rainforest. Home to the majority of Brazil's population, over 85% of this rainforest has been destroyed since the discovery of the Americas by the Europeans. But in recent years, another use of reforestation has been put forward to fight climate change. If this is the goal, then what we're looking for isn't a forest at all, but actually a wetland. And more specifically, a mire or a bog or a muskeg, or what's generally known as a peatland. While maybe not as popular as rainforests, what peatlands lack in charm they make up for in their ability to store carbon. You see, when something like a tree dies in any regular forest, it eventually rots, releasing all the carbon captured during its life back into the atmosphere. In peatlands, however, dead organic matter, and particularly sphagnum moss, finds its way into oxygen-depleted waters, slowing down and even halting the process of decomposition. This leads the organic material to collect and form a substance known as peat, an extremely dense store of carbon. These are the first steps towards truly sequestering carbon from the atmosphere into the subsurface of the Earth. This is also the first step into making fossil fuels, and if enough time went by, the peat would eventually become coal, making it the only substance that is considered both a fossil fuel as well as a slowly renewable resource. But this process can take hundreds to thousands of years, meaning using it to combat climate change on a human timescale isn't really feasible. No matter how they're planted though, every tree will help, which means there's no reason not to donate. If you're a patron of mine, don't worry. I took the money you guys gave me in October and donated to Team Trees, so technically you've already donated as well. But like you just learned, the more trees the better, so feel free to donate more. I know this video is coming out a bit after everyone else put out their videos for the fundraiser, but I had no idea this was going to happen, and it takes time for me to make videos, so here I am a bit late to the party. Either way, I hope you enjoyed, and if you want to see more videos about forests and maybe even hear my voice, there should be a link on screen taking you to a channel that I had to create for my university, so check it out if you want to know what I sound like when not reading a script. Thanks.
Hey, so in my last video I talked about the 10 largest forests on Earth, but there was a little more that I wanted to talk about. Namely, I wanted to add some of the forests that would have made it onto the list in the past, but because of human interactions no longer qualify for it. Forests used to be seen as a rugged wilderness that we humans needed to conquer in order to survive in this world. But as time went on and our dominance over the natural world became apparent, forests became a refuge for wildlife to cower at the destructive powers of man. So, in no particular order, here are the 5 most damaged forests on the planet. Up first is the Atlantic rainforest. When the Portuguese first landed on the continent of South America, it was this forest and not the Amazon that they first encountered and wrote about. Since then, the forest has seen large populations of people come in and threaten the native habitat. Of all the species that called the Atlantic rainforest home, 40% of its vascular plants and 60% of its vertebrate animals are endemic species, meaning they are found nowhere else on Earth. And already, around 250 known animal species have gone extinct here due to human encroachment. This forest was once some of the most diverse rainforest on the earth, contending with the Amazon itself, hosting a total of 20,000 discovered plant species, and in certain areas 450 different types of tree could be found in only a single hectare of land. In what still remains of it, researchers are still discovering new endemic species. From 1990 to 2006, over 1,000 new species of flower alone were recorded in the forest, despite the damage that's been done to it. Even large animals are still being found for the first time here, like the blonde capuchin, which was first discovered in 2006. Once covering 1,315,000 square kilometers on Brazil's eastern coast, this forest would have placed 6th on the top 10 list, just smaller than the Congo rainforest. But now, over 85% of the rainforest has been cleared to make room for pastures and farmland, and nearly all the species that live here are either threatened or endangered. Currently, the forest is too fragmented to give an accurate measurement of its size, and the largest undisturbed patch I could find was less than 7,000 square kilometers. Next is a forest I mentioned several times on my previous list, and that is the Southeast Asian rainforest. Before being developed by humans, this was the largest forest on the planet. Covering most of India, Bangladesh, southern China, all of Southeast Asia, Indonesia, the Philippines, and New Guinea, the total area of this forest came in at over 7 million square kilometers. In comparison, the Amazon, which is the world's biggest forest today, covers only around 5.5 million square kilometers. But with China being the most populated country on Earth, India being the second most, Indonesia being the 4th, Bangladesh being the 8th, the Philippines being the 12th, and Vietnam being the 15th, this is by far the most densely populated area on planet Earth, with nearly half the human population living within this region alone. In order to accommodate billions of people, the land here needed to be cleared for agriculture and living space, and now, the Southeast Asian rainforest only exists in isolated pockets, 3 of which were large enough on their own to make it to the top 10 list individually. This forest was also on par with the Amazon in terms of biodiversity, but has seen much of that diminish as habitat is destroyed to make room for humans. And as populations continue to climb in the area, we can only expect to see the forest continue to disappear. Another forest missing from this list was the North American deciduous forest, which once covered all of the eastern United States and parts of Canada, at roughly an area of 3 million square kilometers. At this size, this would have been the 4th largest forest on the previous list. But, like the other forests, the North American deciduous forest was in the way of dense human settlements and has become too fractured to be considered a single forest. Much of it is now suburban development or farmland with only small parks protecting what remains. A nearly identical case is to be found in the Chinese deciduous forest in central and northern China, where the land was also cleared for the human populations hosted in the region. This is perhaps an even more damaged forest than that of the United States, as China hosts 1 billion more people. But in recent years, China has made great attempts to reverse the damage they've done to their forests, and have launched massive reforestation efforts. Just this year, in fact, China announced plans to reforest 66,000 square kilometers of land. Still, forest once covered more than 2 million square kilometers of China's land area, almost none of which remains today. Lastly is the European deciduous forest. This, along with the Chinese deciduous forest, are probably the oldest examples of mass deforestation by mankind. Like China, forest once covered basically all of Europe outside of the Mediterranean zone, or over 4 million square kilometers. But starting before the Common Era, these forests were cleared to make way for ancient and medieval farmlands, with large portions of it gone before the 1900s. Then, once the Industrial Revolution came along, this process accelerated and Europe was stripped of virtually all of its remaining forest cover, outside of a few strongholds like the forests of Romania or the Scandinavian Russian taiga, which made it onto the previous list. Unfortunately, the damage has already been done to these forests, and they will likely never return while humans still inhabit the Earth. The most we can do now is restrict any further development and try our best to protect the remaining forests of the Earth. I think it's the forests in this video, more so than the ones I mentioned in my last video, that show the true scale of man's impact on the Earth, and are also the ones most in need of protection. Thank you for watching this video, and if you haven't already, check out my previous video where I go through the 10 largest forests on Earth currently. Also, make sure you like this video and subscribe to my channel if you'd like to see more videos like this in the future. Thanks! Forest. Covering 20% of all land on Earth, they are by far the dominant terrestrial biome on the planet, with the majority of both plant and animal species residing within forested areas. Forests create highly productive lands with diverse ecosystems and help to stabilize our climate by producing oxygen and sequestering carbon dioxide. It should suffice to say that forests are among the most important natural features on our planet, and life on Earth wouldn't be the same without them. Unfortunately, this tremendous value has been overlooked in the past centuries as our world's forests have diminished to nearly half the size they once were. Before the Industrial Revolution, forests covered a total area of 60 million square kilometers of the surface of the Earth, which is 40% of all the land surface on the planet. But around the year 1850, as the human population exploded and the demand for space and resources skyrocketed, vast portions of the land were cleared for use in agriculture, human habitation, and resource extraction. Of the 60 million square kilometers of forest that covered the Earth not too long ago, only about 30 million square kilometers remain, and every year around 73,000 square kilometers of forest is lost. So, in honor of some of the Earth's most important and threatened habitat, let's take a look at the 10 largest forests on Earth. Before we start though, I just want to make a quick distinction between a forest and a woodland. To most people, they're synonymous, but there is an actual difference between the two words. Though slightly arbitrary, a woodland is an area with less than half of the ground covered by woody vegetation, like short trees and shrubs, while forests are a lot more dense, typically with taller trees and more than 50% of the ground covered by vegetation. Instead, woodlands are most commonly seen as a transition area between forests and grassland biomes. This definition means most Mediterranean and developed areas won't make it onto this list, as they qualify as woodlands and not true forests. Now that we have that out of the way, let's get started. Number 10 is the Primorye coniferous forest in Russia's far east subject of Primorsky Krai. Being the largest country on Earth, Russia is going to hold a couple of the world's largest forests, and you should expect to see it on this list again. But here, in the Primorye forest, an impressive amount of diversity is to be found, especially when compared to other conifer forests of Russia. This is most likely a result of the fact that this land was avoided by glaciation in the past few ice ages, whereas lands further north became heavily glaciated within the past few thousand years, which prevented the diversification that occurred further south. Living here is the Ussuri black bear, Manchurian sika deer, and an impressive array of great cats, including the Amur leopard, the Eurasian lynx, and the Siberian tiger, where the Primorye forest is actually the last refuge of the extremely endangered tiger, with a maximum population of only around 540 individuals, though fortunately has been stable and increasing since 2005, when the population was only 393. This is also the only place on Earth where bears, tigers, and leopards coexist. This forest is also some of the last habitat for Blakiston's fish owl, the largest owl on Earth. Aside from the Korean pines and Manchurian firs that make up most of the forest, many plants here are relict species found nowhere else on Earth, including several species of fern and lotus plants. Another result of the great diversity found here is that many plants in the Primorye forest also offer medicinal benefits, and research is continually being conducted in this area. Due to its proximity to the Pacific Ocean, the climate here also qualifies as a temperate rainforest, although temperatures vary wildly based on the season, as during the summer nearly tropical conditions persist, while Arctic conditions exist throughout winter. Due to the Primorye's remote location and impressive conservation efforts under the Soviet Union, it has remained almost entirely intact over the years. Only recently have commercial operations started to expand as Russia enters economic hardships. Funding for conservation has fallen from the federal government down to more regional powers, and as a result, the forest is less protected now. However, the area still receives good funding from the international community, and funnily enough, the United States is the greatest donor of funds to help in the preservation of these lands. As a result of these efforts, the Primorye forest is 130,000 square kilometers and consists mostly of old-growth forest. This is an impressively preserved forest and sadly more of an exception to the rule for this list, especially for the next forest. Number 9 is the Burmese tropical rainforest in the modern country of Myanmar. What was once part of the greater Southeast Asian rainforest has sadly now receded into just a few pockets of forest between settlements. This was some of the oldest rainforests on Earth, as the climate here has remained virtually constant for around 140 million years, in part due to its proximity to the coast of the Indian and Pacific Oceans, and its location near the equator. As ice encroached from the North and South poles, many species from the surrounding lands came to this area for refuge, and as a result, the forest became highly diverse over the years, and today the area hosts a wide variety of animals, such as the Asian elephant, Bengal tiger, and the Sunda pangolin, and is especially rich in primate species such as lemurs, macaques, and gibbons, many of which live their entire lives in the canopy, never venturing to the forest floor. Dominant trees here are in the Dipterocarpaceae family, which are emergent trees with the characteristics of being tall and skinny with leaves only at the top. Sadly, these qualities make the trees attractive to loggers for their suitable use in construction. And as I mentioned earlier, this forest used to be part of a far larger ecosystem, and today it continues to shrink due to both legal and illegal logging operations. Myanmar also used to be a highly isolated country which helped protect its forests, but as the nation begins to interact with its neighbors and open itself up to foreign investment, it is likely that the forest becomes burdened with greater reductions in the future. Unless serious conservation efforts are started soon, all of what was once the Great Southeast Asian Rainforest on mainland Asia could be gone in our lifetime. As it stands now, the Burmese rainforest is 233,000 square kilometers, which is much larger than the last entry on this list, but nothing compared to what it once was. Number 8 is the Valdivian Temperate Rainforest. Located in Chile and Argentina, it's not the first rainforest people consider when thinking about South America, but it's still rather impressive. The Valdivian is one of the newest forests on Earth, with the land where it now grows having been completely covered by the Patagonian ice sheets up until around 17,000 years ago. That means this forest hasn't even existed for all of human history. Despite having been covered by glaciers, most of the forest's diversity was preserved in the northern reaches of the forest. And being a vertically arranged forest, there's a good deal of variation in climate and ecosystem type as you change latitudes. In the north is a climate similar to the Mediterranean, which is relatively dry and warm, and the trees are mostly deciduous, meaning they lose their leaves every year, which is another thing that's uncommon in South America. As you move south, the moisture level increases and true temperate rainforests emerge. This is what most of the Valdivian forest consists of. But then further south, the elevation increases and you get a more alpine forest consisting mostly of conifers, similar to the forests of New Zealand. And for some reason, many of the animals found here are quite small, including the kolokolo possum, the pudu, the world's smallest deer, and the codcod, the smallest wildcat in the Americas. Trees here mostly belong to the Nothofagus, the Fitzroya, or bamboo families. Today, little of the Valdivian is protected, and it's currently being logged extensively to use the rich timber. And in the place of the important big trees which take many years to grow are smaller, faster-growing tree species such as eucalyptus, which don't do nearly as good of a job in preserving the habitat here. Despite this threat, however, the Valdivian comes in at around 248,000 square kilometers. Number 7 is the Borneo Tropical Rainforest. This also used to be included in the Southeast Asian rainforest, but has since become isolated into its own ecosystem, located on the third largest island on Earth. Like the Burmese rainforest, the Borneo rainforest is also some of the oldest on Earth, at around 140 million years old. As a result, this area hosts an abundance of biodiversity and endemic species, featuring 10,000 plant species, which includes over 2,000 species of orchid alone. Perhaps the most interesting orchid species found here are the 5 types of Rafflesia flowers, known for smelling strongly of rotting flesh to attract flies for pollination. Within this group of flowers is Rafflesia arnoldii, the largest single flower on the planet, which comes in at roughly a meter in diameter. As for animals, many extremely endangered species call Borneo home. The Sumatran rhinoceros, known for having 2 horns, is the rarest species of rhino to exist, with only about 275 still alive in the wild. Also found here are the critically endangered Bornean orangutan, which are hunted and either captured for sale as pets or killed for their meat. All animals here also suffer from habitat loss, as more of the forest is converted to plantations for rubber and palm oil. And while there are some large nature preserves on the island, such as the Kayan Mentarang National Park and the Bitang Karahoon National Park, much of the forest is still in danger of further reductions. Currently, the rainforest of Borneo is around 290,000 square kilometers, but as this forest accounts for nearly half of the tropical timber trade, it will likely continue to diminish in size unless more is done. Number 6 is right beside Borneo and very similar in a lot of ways, and that is the tropical rainforest of New Guinea, on the second largest island on Earth. But unlike Borneo, the rainforests of New Guinea are mostly preserved, with only the southern regions of the island being developed to any extent. This rainforest can be seen as the largest and greatest bastion of the Southeast Asian rainforest. Here, between 5 and 10% of all the species on Earth reside, roughly equal to all the species found in Australia. And despite being geographically close to Borneo at only 1,300 kilometers away, the animals of New Guinea are more common to those of Australia, as the New Guinean landmass is actually part of the Australian continental plate, and the two lands were once joined into a single continent called Sahul. Species found here include marsupials like tree kangaroos and wallabies, as well as monitor lizards and the Reggiana bird of paradise. However, much of the island remains unexplored, and New Guinea represents some of the greatest opportunities for discovering new species. And on top of being extremely biodiverse, there's also a thriving tribal culture on the island, hosting almost 1,000 different tribes and almost the same number of languages, making the island also the most linguistically diverse place on the planet. And of these tribes, an estimated 44 have remained uncontacted by outsiders to this day. Due to the roughness of the land and the low populations hosted here, the rainforest of New Guinea has remained virtually intact at 545,000 square kilometers. Okay, we're halfway through this list and we're beginning to reach the truly massive forests of Earth. At number 5, we have the Congo Tropical Rainforest. And like its name suggests, the Congo rainforest closely surrounds the Congo River, but also spans into 7 other African nations. It is here in this forest that many iconic African animals live, including some of the world's largest primates, like chimpanzees, gorillas, and bonobos, as well as other ginormous animals like hippopotamus and African elephants, which is the biggest land animal on Earth. Sadly, there are high rates of poaching and theft of animals for international trade here, and many animals need armed guards to remain undisturbed. Like New Guinea, there's also a good amount of indigenous human habitation here without causing degradation to the forest. Tribes here include the Ba'aka, the Ba'umbuti, the Efi people, and around 150 more, and many of these people have been classified as a race known as Pygmy, which are distinct from surrounding Africans, and are known for being far shorter than average heights. Although the forest is not very diverse, having a biodiversity lower than any other forest mentioned on this list so far, it is extremely dense and difficult to navigate. It was the inspiration for Joseph Conrad's famous book, Heart of Darkness, and is seldom traversed by people who do not live here. As a result, the Congo rainforest has also remained roughly intact through industrialization, and in fact it has some of the lowest deforestation rates of any major world rainforest. However, this area is also very rich in resources such as oil, diamonds, and gold, and the rainforest lies within some of the poorest countries on Earth. Because of this, the rainforest may soon face new threats of development and resource extraction, and in the future more will need to be done to ensure the protection of these lands. Still, the Congo rainforest remains the second largest rainforest on Earth at 1,780,000 square kilometers. The next 3 forests were all once part of a single continuous band around the Earth, much like how the Burmese, Borneo, and New Guinea forests were all part of the Southeast Asian rainforest. But unlike it, this forest has become broken up not because of human encroachment, but rather because of changing sea levels and climate. The 4th, 3rd, and 2nd largest forests on Earth, respectively, are the Scandinavian Russian taiga, the East Siberian taiga, and the Canadian Boreal forest, collectively called taiga, and they constitute the largest biome on Earth outside of the oceans. While the Scandinavian taiga is the smallest of the 3, it's still the largest biome of Europe, and one of the last true wildernesses to be found on the continent. Here, the trees are an equal mix of spruce, pines, and birch. In the eastern Siberian taiga, also found almost entirely within the borders of Russia, the forest is largely dominated by larch trees, and while the Canadian Boreal forest stretches from Alaska to Quebec, it consists mostly of spruce trees. The fauna found in all 3 of these forests is also pretty similar, where you'll find moose, reindeer, black, brown, Asiatic, and polar bears, wood bison, Canadian and Eurasian lynx, foxes, wolves, wolverines, just a bunch of different salamanders and toads, and most impactful out of them all, beavers. Despite their size though, the taiga forests are fairly poor in terms of biodiversity, and this can be attributed to the most recent ice ages, as all these lands were covered by glaciers as recently as 2.6 million years ago during the Pleistocene epoch. Therefore, species here haven't had the same amount of time as tropical species to specialize and speciate. Among the forests on this list, the taiga definitely has the most harsh climate conditions, as the taiga hugs the Arctic Circle and several months out of the year are spent under several feet of snow. At times, the taiga can even become colder than the tundra, and the coldest temperature ever recorded in the northern hemisphere at -68 degrees Celsius was in the Russian taiga in the town of Oymyakon. Taiga forests are also very important when talking about the climate, as these forests sequester more carbon out of the atmosphere than all of the tropical and temperate forests combined. Conservation of these areas in the past has been successful, as the Soviet Union put harsh restrictions on the use of their taiga. But that has begun to change, again due to Russia's recent economic downturn. Entrepreneurs from China have begun to look to Siberia to fuel the huge demand for timber in their country, and most of the forests of Canada are unprotected and open for harvesting as well, with only around 8% of the forests here protected by the government. But there are regulations to at least make sure companies rehabilitate the land once they've used it. Together, this single biome and these 3 forests account for 30% of the Earth's total forests, and take 3 of the top 4 places on this list, with the Scandinavian Russian taiga at 2,156,000 square kilometers, the East Siberian taiga at 3,900,000 square kilometers, and the Canadian boreal forest on top at a whopping 4,200,000 square kilometers. And while all 3 are impressive, there's still one more forest that beats them all. At number 1, you've probably guessed it by now, is the Amazon tropical rainforest. Covering land in 9 nations, the Amazon represents more than half of the world's remaining rainforest. Not only is the Amazon the world's largest rainforest, it's also the most biodiverse, with 1 in 10 species on the planet existing here and nowhere else, including 1 in 5 bird species on Earth, and even 1 in 5 fish species on the planet live within the Amazon River network. Together, the Amazon is the world's largest collection of plants and animals, with 16,000 species of tree alone, and current estimates project there to be 390 billion trees to exist within the forest. Animals found here include the jaguar, the anaconda, anteaters, spider monkeys, poison dart frogs, iguanas, macaws, toucans, parakeets, the brown-throated sloth, and so many more. There are many theories as to why this region is so dense with endemic species found nowhere else on Earth, and most have to do with the age of the Amazon rainforest itself, which is around 55 million years old. In the past, rainforest encompassed nearly all of North and South America, and many different species spread across these different lands. But as the climate cooled during the Eocene epoch, something I covered in great detail in my last video, the forest shrank to where it is now, and all the species contained within either had to retreat or die off. Currently, we are seeing the further shrinking of the Amazon rainforest, not due to the climate, but as a result of human interaction, and the Amazon has already lost 20% of its area, or nearly 800,000 square kilometers. That's more area than the Primorje, Burmese, and Valdivian forests combined. Most of the forest being cleared is to make room for cattle pastures or soy farming, but once cleared of its forest, the Amazonian soil quickly loses its fertility, and in order to continue to grow crops here, farmers will continually burn and clear new sections of land, leaving the old ones to wither. And now, the deforestation of the Amazon can even be seen from space. What has been done to sections of the Amazon has been deemed by some as ecocide. To make things even worse, as more forest is cleared, moisture given off by evapotranspiration diminishes, and fewer inches of overall rainfall come to the region, making agriculture logistically unsustainable and making it harder for new forest to grow back. There is actually surprisingly little economic benefit for clearing the forest for pastoral fields, despite what many might think, and as more of the forest is destroyed, the land becomes overall less productive. Interestingly, according to a study, if left intact, a single hectare of the forest could produce a revenue of up to $6,800 a year if it's sustainably harvested for the fruit and down timber, compared to only $1,000 per hectare if it's cleared for commercial timber, and only $148 if the land is cleared for cattle pastures, which is what 90% of the forest is being cleared for. Currently, only around 1,730,000 square kilometers are protected, which is roughly the same size as the entire Congo rainforest, but less than half of the Amazon's total area. Fortunately, people are beginning to recognize that maybe protecting the world's most important ecosystem is a good idea, and conserved land is increasing fast, while deforestation rates have dropped to only around 5,000 square kilometers a year, from a high of 27,000 in 2004. Someday, hopefully soon, we'll get those numbers down to 0, or even better, begin replanting and restoring parts of the Amazon that have already been destroyed. As it stands now, however, the Amazon is still the largest forest on Earth, measuring up to 5,500,000 square kilometers. That's roughly the same size as the entire United States, including Alaska. In all, the Amazon rainforest represents more than half of the world's remaining rainforest, and remains a stronghold of wilderness in this rapidly developing world. Thanks for watching this video, hopefully you enjoyed it, and if you'd like to help the cause of protecting what remains of the world's forest, you can donate to places like the World Land Trust, the Rainforest Trust, and the World Wildlife Fund, which do great work in purchasing and protecting endangered lands from further destruction. Also, please consider liking this video or even subscribing to my channel. This video took a lot of time to research, and most of the information on the internet is either misleading or wrong, and what I ended up doing was tracing each forest on Google Earth to get an accurate number. I'll be coming out with more videos like this each week, so please subscribe if you're interested in that. Next week's video will be about what forests didn't make it onto this list, so make sure to check in then. Thanks. If you've watched a lot of my videos, you'll probably know how important forests are, and perhaps the most important is the Amazon rainforest, the biggest, most biodiverse, and most valuable terrestrial ecosystem on the planet. Of course, you'll probably also know that the Amazon rainforest continues to shrink as economic pressures force countries to clear-cut the forest in favor of profitable enterprises like selling timber and growing cattle. Without an economic incentive to protect the forest, it's likely that this trend will continue. But if a way of not only making money, but making more money from sustainable practices involving the rainforest were to be brought forth, the Amazon, and hopefully other rainforests as well, would have a much better chance at surviving our industrialized world. With that in mind, here's how to profit by saving the Amazon rainforest. So you can typically divide forest resources into two categories: timber, which can produce saw logs used for construction, and the smaller branches and twigs, which are used for pulpwood to make paper products. But then we also have non-wood products, mostly fruits used for eating, and latex rubber extracts used for whatever we use latex for. The harvesting of non-wood products is usually harmless to the trees and leaves the forest as a whole largely unchanged, while of course the cutting of trees for timber is highly damaging. Unfortunately, for the most part, these non-wood products have been ignored for the easy profits that come with logging. But this may be a mistake. Alright, so it's hard to talk about the Amazon as a whole because the region is roughly 5.5 million square kilometers in area, and there's a lot of variation here. So for our purposes, we'll be using the species found in a survey of this area along the Rio Nanay, running through the Peruvian portion of the Amazon rainforest. Here, it rains roughly 370 centimeters a year, and the plants grow on top of relatively infertile white sand. A survey of just a single hectare showed there to be a total over 275 different tree species present, with about 850 individual trees. Of these trees, 41% offer some kind of market value, or in other words, the products of roughly 350 trees can be sold at nearby markets. Of the 275 tree species, 12 produce non-wood products while 60 produce commercial timber. Not looking so good right now, but hang in there. Of the 12 valuable non-wood producing species, 11 produce fruits and 1 produces latex. It should be noted that there are other species found here that could not be accounted for, but are still valuable if collected. This would include several medicinal plants, fruit-producing vines, and other types of small palms. But of these 12 trees, the most valuable by far is the aguaje tree. Only 8 of these were found in the allotted 1 hectare, but each one can produce about 89 kilograms of fruit, called buruti. That's over 710 kilograms of fruit. And at $10 every 40 kilogram, that totals up to roughly $178 total. Also notable is the naranjo podrido, which translates into rotten orange, and can produce 150 fruits each. 3 of these trees were found, and with the price of each fruit being 25 cents, the naranjo podrido adds about $113 in value to a single hectare. The ungurohui was also a very common tree here, with 36 total individuals in the given area. Each tree can produce almost 37 kilograms of fruit called patawa. Patawas can be used to produce patawa oil used for cooking or for cosmetics, mostly for softening hair, and even has medicinal applications like treating bronchitis. At $3.50 for every 40 kilograms of patawa, ungurohui trees end up adding $117 to the forest's value. In total, all the fruits and latex from just a single hectare of Amazonian rainforest can provide a value of $698 US. Not too bad. Now let's take a look at timber. I know I said 60 species of tree produce timber here, but many are the same genus, so to make things easier, I'll be using commercial names, some of which include several species under a single name. I'll also only be showing the trees with a total value of $5 or more, just to keep things simple again. One last thing before we begin, it should be known that the task of extracting and transporting timber is costly compared to picking fruit, and because we're out for profits here, I'll be taking 40% out of the final values to pay for labor, machinery, and transport. So there are 16 commercial tree types that provide valuable timber, and the most valuable of these is the kumala tree. 83 individuals were found in our single hectare, the most common tree in the forest by far, and offered an estimated value of 19.77 cubic meters of lumber. At $19 per cubic meter, the kumala tree's lumber is worth about $376. Taking 40% off for labor and transport costs, that comes to roughly $225. Close behind the kumala tree is the machinga tree. Although far fewer of them were found, only 10, they grow much larger and therefore provided a greater volume of lumber, almost 25 cubic meters. Because of this, the wood is fairly cheap at less than $15 a cubic meter. But this still made the machinga tree worth almost $219. The quinea tree has some of the most valuable timber, costing $32 per cubic meter, and is also fairly numerous, with 34 growing in our given area. In all, the quinea provide a value of $175 to the forest. Here's the rest of the values. I covered the most valuable ones, the rest are worth a fair amount less. But if you total all these up, you'll get a value of $983 per hectare of forest. Okay, so yes, the timber initially is worth more than all the non-wood products for a single year. But it's important to remember that once a forest is cleared, it's not growing back, while picking the fruits and harvesting rubber isn't nearly as damaging. In just 2 years, you'll have made more money by picking fruit than simply clear-cutting the land. In 15 years, the value extracted from non-wood products will be 10 times the value of the wood extracted from the forest. So, in terms of long-term investment, non-wood products are definitely the way to go. But if you really know forest ecology, you'll know that picking 100% of the fruits produced is in fact damaging to an ecosystem. You see, over time, trees will always die naturally, and if there are no fruits to replace these, the forest will slowly thin out and eventually disappear. So we're not done yet. To keep the forest thriving, we'll leave 25% of the fruit crop behind to replenish any fallen trees. This would also help any animals relying on the fruits to survive. To make the math simpler, we'll include the latex trees under this too. This gives us an annual revenue of about $524 worth of fruit and latex, which means still, after only 2 years, you will have come out on top compared to clear cutting. Okay, but now you must be saying, well, sure, they do clear the forest, but then they use the land for agriculture, and that's where the real money is made. Which is a fair point and what we need to look at next. Today, the cleared land is overwhelmingly dedicated to cattle pastures, so we'll take a closer look at that. Because cows take multiple years to reach maturity, require large amounts of water and food, expensive growth hormones are typically used, and need lots of space to graze, the revenue per hectare raising cattle is actually quite low. Reportedly, it's only around $148 per hectare per year. So even if you clear-cut the forest and raised cattle every year after that, the harvesting of non-wood products like fruits and latex would still offer greater revenue, all the while being a sustainable alternative. But now the question stands, if this is such a profitable enterprise, why does no one do it? Well, first off, people in fact do this. Subsistence farmers and forest collectors simply sell to local markets, whereas large industrial timber companies sell their products worldwide, attracting investment, driving foreign exchange, and gaining the support of federal governments. Also equally important is the level of education required for each task. Clear-cutting a forest requires little more than knowledge on how to operate a machine, and for the most part, if left alone, most cattle will take care of themselves. Knowing exactly what to pick, where to find it, when it fruits, and so on requires a lot more education and time in the rainforest. Without a system to educate and encourage such practices from forming, current methods will persist. But there you have it. That's how you can profit by saving the rainforest. One last thing before going to the end screen, all this came from a paper published in Nature magazine in 1989. In the time since it's been published, not only the prices but the world has changed. I tried to update the numbers, but some figures they learned by literally traveling to the Amazon and asking locals. Being unable to find all the numbers or travel to the Amazon myself, I didn't want to be comparing any 2018 numbers to 1989 numbers, so I kept all the numbers from the paper. Everything should work out roughly the same if updated, but it won't be exact. If anyone can come up with an updated list of prices, I would love to see it. Anyway, I hope you enjoyed. If you did and you want more people to see this, give this video a like. If you want to see more videos like this, consider subscribing. If you want updates on videos, you can follow me on Twitter. Other than that, another video is coming next week. Thanks for watching.
This lesson was prepared by Jacqueline Heinel and Sam Drurup as part of the National Science Foundation supported Boat of Knowledge in the Science Classroom books. This lesson covers the topic of tree identification. This lesson is to be presented in conjunction with hands-on leaf identification activities. By the end of today's lesson, you will be able to identify trees commonly found in the state of Ohio using an online dichotomous key. A dichotomous key asks you specific questions with 1 or 2 answers and will allow you to narrow down the possible trees based on leaf morphology. 4 basic parts of the tree that can be used to determine the type of tree you are looking at. First is the bark, the outermost layer. Tree species will have distinctive bark characteristics. The stem, smaller branches where leaves attach, can also be indicative of tree species such as maple, ash, dogwood, or buckeye. These trees all have opposite branching patterns. Leaves are the part of the tree that converts solar energy into sugars. These are the most distinctive morphological features for identification, but are seasonal in deciduous trees. Flowers and fruits are the reproductive structure and product of a tree. They are also very useful in tree identification, but are much less reliable and rarely found on the tree themselves. Today we will be using leaves to identify the species of tree. There are two main types of trees, coniferous and deciduous. Coniferous trees, like pines and firs, have specialized leaves, or needles, that remain on the tree year-round. Deciduous trees lose their leaves every year in Ohio in the fall. Deciduous trees occupy a specific niche. They occur readily in forests with an average temperature near 50 degrees Fahrenheit with 30 to 60 inches of precipitation a year. These areas also have 4 distinct seasons: spring, summer, autumn, and winter. It is during the autumn season when deciduous trees lose their leaves. This map shows where deciduous forests can be located worldwide. As we can see, deciduous forests can be found across the eastern half of the United States. There are two main types of deciduous leaves, simple and compound. A simple leaf has a single leaflet attached to a branch via a petiole. A compound leaf is one with multiple leaflets attached to a single petiole. It is important to note that the petioles are different than stems, as they are not woody. Common forest type we have in southeastern Ohio are mixed oaks forest, and in the northwest are largely beech or elm ash swamps. The difference in forest type is largely due to the difference in geology and soil age between glaciated and unglaciated parts of the state. We will now walk through an example of how to use the online leaf dichotomous key to identify a tree of interest. This key can be found at www.olin.org/tree/index.html. First, we will select the Identify by Leaf option. Please note you can also use this site to identify tree by FruitNet following the same procedure. You will advance through the dichotomous key, clicking on the image of the correct answer when describing your leaf. Please note that the questions will change depending on how you answer the previous questions. In regards to the type of leaf, you will decide if the leaf is a needle, scale, broad, or flattened. In this example, the leaf can be described as broad. Question asks if the leaf is compound, many leaflets on a single petiole, or simple, a single leaflet on a single petiole. In this example, the leaf we are looking at is a compound leaf. We are then asked about the margins of the leaf, or the edge of the leaf. Is it coarsely toothed, smooth, or toothed? In our example, the leaf is serrated, or toothed. We are then asked about the relative size and shape of our leaflets. Our leaf has leaflets that are larger on the distal end of the leaf compared to the basal leaflets. Next, you are asked to count the leaflets. Our leaf has 5 to 7 leaflets attached to a single petiole. Now that we have narrowed the options to shagbark hickory and pignut hickory, as our leaf is 12 to 20 inches long, we conclude that the leaf we are looking at came from a shagbark hickory. When you select shagbark hickory, we are then taken to a page that describes the leaf and fruit characteristics as well as a general description of the tree. Continue using this dichotomous key to identify the types of leaves you have collected.
Hey, check it out. I found poison ivy. Hey y'all, I'm James Wright and welcome to my woods. Today I want to take you out on a special adventure and we're going to go out and walk through the woods and identify some trees and show you some ways that you can use to identify trees. And I'm out here with my son Arthur. Say hi, Arthur.
Hi.
And the two of us are going to have a little fun here. So let's go off into the woods and see what we can see. So first of all, this is the absolute best time of the year to come out and identify trees. It is not winter yet. The leaves are still fairly green, but starting to change. Some of them starting to fall. There's fruit on the trees, fruit on the ground, and we can walk around and quickly and easily identify them. Now, one I see right here is red oak. You can see how these have very pointy leaves. So here I have two trees right next to each other. This one right here and this one right here, and they both are oak trees, and they've become very, very obvious and easy to identify once you see them. The bark on these two is a little bit different. This one is older, so it's a little more shaggy, kind of harder to identify. Whereas this one, you have a little bit more of that standard oak look. Let me take you over here and show you basically one of the reasons why this is a great time of year to come out and identify trees is you get to identify their fruit and their leaves that are down on the ground. So here I have, this is from the first one over on my right, and this is from the one on the left. You can see how all these have rounded ends on them. And then all of these have these pointy ends. The pointy are from the red oak. Anything that's rounded are white oak. Also, you can look at the acorn, and the acorn from the red oak is usually a very smooth cap, not much identification to it, whereas the white oak usually has either a very bumpy cap or it's a very hairy cap. And a lot of times the hair will actually hang down over, especially with the bur oak and swamp oak. So let's go take a look at some others. Here's one that I like. This bark, it looks fairly similar to oak in many respects, but you'll see these leaves come off and it'll be a group of 5 leaves, 5 or 7 sometimes. Like on this one, you can see how they bunch out more. But here's the ash leaf, and they come in these whole series. You might think that those are 7 leaves, but this is actually 1 leaf that joins back at the stem. Ash is a very easy one to identify by the leaf. So here's one that is a bit confusing. They may look like ash leaves that we just looked at. They're clustered together in 7. They're from a single bunch on the stem, but they're not ash. This is actually a type of maple. It is a box elder. And after a little while, you're going to get very used to identifying box elder by the branches and tree. You'll often see this very distinctive bark and all of these little sprigs coming off everywhere. That's a very common representation of box elder. Very knotty, very twisty. It's not a hard maple, but it is a really nice maple with a lot of color in it. Sometimes you get a red flame through it. A very beautiful wood to work with and would make a great workbench in my mind. But yeah, box elder is a type of maple, often called ash leaf maple, because the leaves, well, they kind of have a look of ash to them. Another thing I'm doing is I'm walking along and I'm looking for acorns, I'm looking for nuts, I'm looking for leaves, and I'm starting to identify the leaves. Like this one is a type of maple, that's a type of oak, and usually from the ground you can start to see where the leaves are, and then you can look up into the trees and find out where are they. Does that leaf look like the one I'm putting on the ground, or does that leaf over there look like the one on the ground? And then from there you can identify the bark on the tree and say, oh, I know what that is now. So we've been looking at hardwoods, but here you have a couple softwoods. This is a fir, and then you come back over here, and this is a bark that you'll know quite a bit. This is a pine tree. And I don't know as much about them because I don't use the wood as much and they don't interest me as much. But one of the things that's actually kind of fun for me are the needles, particularly from the white pine, because they're very long needles like that, and you'll find that they each have 5 sprigs, which is white, W-I-T-E, 5 letters, 5 sprigs, a fairly easy one to identify, and one of my favorite pines. Okay, here's one that I really like. You'll find these heart-shaped leaves, and they fall in great clumps. They don't change color that much, and they clutter the ground. And you're also going to find these sticks that have a lot of nubs and knobbles on them, and these sticks are very telltale of cottonwood. So let's look around here. We found these all over the ground. and we're going to look around for usually a very large tree, and voila, there it is. This has a lot of bark twisting on it. They usually end up having a very, very straight, long trunk all the way up. And you can see they have a very large canopy most of the time. It's cottonwood. In early spring, their seed will come floating down through the air in little tufts of cotton, but they are very, very easy to identify in the fall or anytime by these leaves. Not too many trees have leaves like these heart-shaped cottonwood leaves, like that right there. So here's one of my favorites. You'll be walking along the path and you'll come across these nuts. They're kind of split four ways. The husk falls off very easily, and then you'll have these white nuts underneath. These are hickory nuts, and hickory is one of my favorite woods. Beautiful, beautiful wood, extremely hard, great for axe handles and anything you don't want to break. Just a great, great wood all around. But one of the cool things about it is the bark is very easy to identify. The bark here is actually this kind of shaggy thing that, well, it just like these pieces will flake off. And this is a hickory tree. Now, if you go all the way up, then you get this almost, these things are huge, and I'm trying to find one here on the ground, but they're about 12 inches long. So each one of those are about a foot long. They're huge, huge leaves. And you can see that each one of them has a cluster of 3 and then the stem coming off. That's one leaf, is that cluster of 3 and the stem. And this one over here has 5 and 1 long stem. So they're a very beautiful tree, great wood to work with, and a lot of fun when you identify them. Plus, hickory nuts taste good, and you can take those home and have fun with them. So yeah, I'm always finding these when I'm out running in the woods. You will stumble across them, and it's a very obvious point that there's a hickory tree here. So here's another one. You're going to find these oval leaves quite often. I'll be looking around and there's one here and one here, and there's another one over here and here and here. And they're fairly oval. Some of them have a very fine sawtooth like this one. Some of them have a very pronounced sawtooth. But then you also see these trees that if you didn't know any better, you'd swear they were a pine tree. They kind of have that shaggy bark that you see very commonly in pine trees. That is actually a cherry tree. And a cherry is a fantastic hardwood for hand tools. Just a beautiful, beautiful wood with a dark red color, and one of my favorites. But yeah, you'll be looking along the floor, and you'll come across all these little yellow, tiny little leaves like that one there and that one there. They're cherry leaves. Now here's another one I want to identify. This isn't a tree, but if you're wandering around the woods, it's a good one to know. And you'll see these 3 leaves here, and often they look like a mitten. And the one in the middle will have a thumb on both sides, whereas the one on the outside will just have a thumb on the outside. That is poison ivy. And yeah, don't go rubbing in that. Yeah, you'll find this all over the place. So poison ivy, poison ivy, poison ivy, poison ivy. Yep, when you're wandering the woods, that's a good one to know. Okay, here's a fun one. So you're walking around the woods and you find this hickory nut. And then a little while later, you find this one and you think, oh, is that a black walnut? No, it's a hickory nut. If you look closely, it's got this cross section at the top. It's just one that hasn't turned black yet, hadn't gotten soft, so you can pop off the husk. A walnut, though, a black walnut looks like this. A little smaller than a baseball. When they come down, they're green, and then they slowly turn black. And then eventually, the black all falls off, and you'll see this traditional, or like a walnut inside. The leaves look kind of like an ash leaf in that they're all one big piece. And they have these sprigs that come off, but they're very hairy, they're fuzzy, and they have this like characteristic to them. The center of the stick is very pithy, and then the bark is very easy to identify. It comes like this. You see this crisscross X shape on the bark, and that is very characteristic of a walnut tree. And so you know this right behind the bark, there's a bit of a white wood, the sapwood, and then inside of it, you're going to have that very, very dark walnut wood. And then the very core, you're going to have this almost empty core running all the way up the middle in the heart of the tree. So yeah, when you're running through the woods, you're going to come across these nuts, and they become a problem for stepping on because you step on them, you roll. But this is black walnut, and once you start to identify it, you'll be very, very happy you did, because everybody likes black walnut. Now here's one that I should know. It has a sawtooth leaf, and all the spines come back to the central point, as opposed to all coming to the base. They all come back to the main spine. and I'm seeing this tree quite often, and I've seen these leaves a lot. They are all over the place, and you can get a closer look at what the canopy looks like. Well, kind of. But these leaves are just covering the trees, and they're all over the ground. So when I get back to my house, I'll show you how I look that up and identify the tree. So now let me take you to a few sites and apps that I use to help me find what is this plant, what is this tree. And my first and foremost is the Arbor Day Foundation, arborday.org. And I'll leave a link to all of these apps and websites down below so you can go and look at that. And this one is very good, particularly if you live in the US or Canada, at finding native trees. And so it's, asking you, are you in the West Coast, are you in the East Coast, and picking from there. If you're not in North America, then this is going to be a little bit more difficult for you, but it's still fairly doable because it does have trees that aren't just in North America, although it is designed for the native trees to North America. So this will basically then go through, is it is it needles? Does it have cones? Is it a regular leaf? Is it a standard leaf, or is it a compound leaf? It's a standard leaf. Are the leaves directly across the stem, or are they alternating across the stem? And you can go on down through this, and it will give you more and more ideas about what it is until eventually you come to it. This particular one is a little bit deeper down, so rather than dragging you through that, I'll just take you to the answer. It's an elm tree, particularly a rock elm, and this is a fairly common one around here. This is actually what my table is going to be made out of. My dining room table I'll be making here soon. Very easily notified by the paper seeds. You'll find the seed in the middle of the paper, and it's a fairly common tree around here. Then the other place that I often go to and I want to find out more information about is Wiki. A ton of information on there for more information about what the tree is from, history of the name, history about the tree that might be used in different things, far more specifics about where is it located, where is it commonly found, other uses for it and things like that. Wiki is a great place. Google search in general, if you're looking for information, or you kind of know what it is and you're looking for, it's an elm tree, but what type of elm is it? I'll look up elm tree types, leaves, and it'll give me pictures of all those, and I can kind of match them up and get a better idea from that. Another one that I use all the time is British Trees. This is an app you can put on your phone. It is focused on trees in Britain, but I'll even find native trees from America listed there, except for they'll be listed as ornamental trees, or trees that have been transplanted into the garden as opposed to native trees. And this one is great because it's far easier to get around than the Arbor Day, because there's pictures for everything. So if you're trying to find something, this is an app that I use all the time. This is the one I probably use on the fly the most. Then probably the easiest of all of them is PlantNet, with an @ symbol in plant. And this one is so simple because you just take a picture of the tree itself. You take a picture of the leaf or the bud or the fruit, and it goes through the algorithm and tries to figure out just from the picture itself. So it's kind of reading the picture. It's very quick, very easy, and it gives you a general idea. At least it gives you to a point where you can jump off and you can go and you can Google, or you have more information when you go to Arbor Day to look it up. So these are the ones that I use the most. I really don't use that much more, and if I can't find it from these, then I post a picture on social media and say, hey, does anyone out there know what this is? And usually someone's going to be telling me by the end of the day. So there you have it. Next time you're wandering around in the woods, you know exactly how to look up and find out, what is that tree? What is that nut I find? I definitely say go out and explore. The only way you're going to get good at learning what trees are out there is to go out and to experiment, to find out the tree, and to learn. And even if you run into problems and you can't find it online, you can't find it on the apps, and you have no idea what this is, post a picture of the leaf on Instagram or social media and ask people, hey, anyone have an idea what this is? That's a great way to learn as well. So I hope you like this. I do want to say thank you to the patrons on Patreon. You guys are really the reason why I can keep putting out videos like this. If you'd like to see more like this, you can help out with Patreon or find out more about it right down here. Also, if you'd like to subscribe or see some behind the scenes footage, you can do that as well. That's about it for today. And until next time, have a wonderful day.
The Columbian discovery of the Americas was one of the most important and revolutionary events in the history of humanity. On a single day, October 12, 1492, the size of the world doubled, and Christopher Columbus, the leader of this expedition, went down in history both famous and infamous as the man who discovered America. This historic event should be recognized as the catalyst which saw our world changed forever, for better or for worse. That being said, it may not have been the true first time humans from the old world sailed across the ocean, and it's actually well known that Columbus wasn't the first European to reach the Americas at all. The Vikings had already colonized Iceland and Greenland roughly a millennium ago by the year 950 CE. By 999 CE, Leif Erikson is known to have left Norway on his way to convert Greenland to Christianity, and was blown off course, and as a result found a new landmass, which he eventually came back to explore, making it as far down as New Brunswick in Canada. The settlements he built here were only temporary, and after trade with the natives turned up unsuccessful, Erikson returned to Greenland unaware of the scope of his discovery. Evidence for this voyage include the ruins of Viking settlements at the L'Anse aux Meadows, as well as historical accounts of the journey. This, by most definitions, is the only definitively proven contact between the Old and the New World prior to the voyage of Columbus. But that doesn't mean there isn't some evidence that points towards earlier discovery events. Sticking with European exploration, there are some that believe the Romans could have made it to the Americas thousands of years ago. As it stands currently, we have evidence that the Romans made it as far as the Canary Islands off the coast of Africa, which are still over 4,000 kilometers away from the nearest portion of mainland America. Most potential evidence that Romans made this nearly 4,000 kilometer voyage comes from objects found throughout the New World which resemble the craftsmanship of the Romans more than any other Native American style. Perhaps the most popular example is the Skaksik Kalixtihuaca head, or however you say it, I can't pretend I actually know. The artifact in question was discovered in a burial offering dated from between 1476 before Columbus and 1510 after Columbus. The terracotta head shows what many consider to be particularly European features and doesn't match any known native art styles. After analysis by several art historians and archaeological experts, it was concluded that the figure was at least compatible with Roman sculpture styles from around the 2nd century. That being said, many have called into question the artifact's authenticity, or have even suggested it found its way here after Columbus arrived. Another popularly cited example of out-of-place artifacts was found in Guanabara Bay in modern-day Brazil. Beneath the waters here, remains of a shipwreck were uncovered in the late 1970s and continued to be found into the 2000s. Found among the shipwreck were the littering of many ceramic jars. After being analyzed by experts, these jars were identified as likely being amphorae, a container type used commonly by Greeks and Romans. These amphorae were so regular, in fact, that it was common practice for a trading ship to just dump them in the water near where they anchored because it was easier and faster to sail without them weighing down a vessel once they had been emptied. Fragments from an estimated 200 amphorae were found under the waters of this bay in Brazil, and some have used this to suggest that Romans were trading with the natives of this region. Other explanations have been given, however, including a merchant ship being blown off course on its way to the Canary Islands, or even the wreckage of a ship being deposited here by ocean currents. While there are plenty of other theories involving the ancient Europeans and especially the Romans, the next ones I want to talk about comes from the Irish. To understand this one, first we need to learn about an old Irish writing system called Ogham. This language began to develop around 500 CE and made use of many lines carved into a pillar to represent different letters. This is still considered one of the most unique writing systems ever devised by humans and is unlike any other writing system ever studied. So when rock carvings like these, dated between 500 and 700 CE, were found in locations throughout Virginia and West Virginia in North America, it made many people question if there could have been some kind of Irish influence almost 5,000 kilometers away from Ireland. But for the most part, these claims are largely unsupported in the scientific community, although no other idea is popularly supported either. The interesting part of this, however, well actually this is all interesting, but the really interesting part, I guess, is that the Irish have a completely separate story that's been passed down through the generations, which some believe is connected to this story. The tale involves Saint Brendan, an Irish monk said to have sailed across the Atlantic to discover paradise. Roughly around the same time these markings were estimated to have been made. The story is pretty long, but in short, Saint Brendan leaves Ireland with 14 other monks to discover new lands called the Isle of the Blessed. While on this journey, Brendan and the 14 monks and a couple of latecomers encounter some strange animals, some familiar ones too. They run into a few people, some described as having darker skin complexion, and they generally get into shenanigans until Brendan and the rest of his posse decide to head back home. On the way, it's said that they passed an island of blacksmiths who tossed molten slag out at their ship, and then they passed by crystal pillars. The island of blacksmiths is thought to be an interpretation of the volcanic island of Iceland, spewing out molten rocks as they sailed by, while the crystal pillars is thought to be an allusion to floating icebergs found throughout the North Atlantic. To add a cherry on top of all of this, in 1977, the British explorer Tim Severin completed a voyage from Ireland to America using only a traditional Irish kirk boat, proving that at the very least this trip, and therefore this story, was possible. Of course, lines marked on a cave and an old Irish imrim aren't exactly hard evidence, and if none of these seem very possible still, then we're going to need to leave Europe. In fact, ideas about Africans reaching the Americas before Columbus are equally numerous and might even be more convincing. Before I get to them though, I just want to look at the geography of this a bit, hope you don't mind. Because when you take a real look at things, Africa and South America aren't actually terribly far apart from one another. The closest tips of each continent are less than 3,000 kilometers away, but off the coast of Africa are also the Cape Verde Islands that make a suitable restocking station. If launched from here, the trip to South America would be less than 2,600 kilometers. Not to mention, if you look at prevailing wind patterns over this part of the world, we can see that winds around the equatorial Atlantic all blow from Africa to South America. These are what's called the northeast trade winds. Trade winds because they're the same winds that were later used by Europeans during the times of the Columbian Exchange and colonization. What this means is that sailing across this sizable gap could be fast and efficient if explorers had a good understanding of the winds in the area. So it's no surprise that talk of Africans reaching America before Europeans started as far back as 1862, when the first colossal head of the ancient Mesoamerican Olmec civilization was discovered in modern-day Mexico. When analyzing the facial features displayed on these heads, it was noted how similar they looked not to the native people but to Africans, and it was suggested that the heads were either created with Africans in mind or by Africans themselves who had traveled here. Now, these ideas have been heavily rejected by much of the scholarly community, but it has left the question of African activity in America open, and since then other theories have emerged. It's commonly believed that Native American populations came across the now underwater land bridge of Beringia, which once connected Alaska to Siberia. And this has been more or less confirmed by genetic analysis, showing Native Americans' closest relatives to be those genetic groups from Eastern Asia. But what's strange is that many of the oldest human remains uncovered in the Americas come not from the land around Beringia, but rather further south, towards the middle of the landmass. The most well-known example of this are the remains of a teenage girl, nicknamed Naya, found in the Yucatan Peninsula in modern-day Mexico, nowhere near where humans supposedly first stepped foot on the continent. The bones left by this unfortunate girl and those of other early inhabitants of America were found to have completely different bone structures from the Native Americans later found by Columbus. Instead, their faces were smaller and shorter, while their entire skulls were longer and narrower than the typical Native American. Reconstructions of the girl's face revealed these differences much clearer, for me anyway, and show just how these features are much more in line with those of a person of African descent, as well as possibly Native Australian or Pacific Islander. This isn't the only fossil like this discovered in America either, and the finding of similar ones, all older than the ones found in Beringia, has called into question whether those Asian explorers who crossed Beringia really were the first people to walk on American soil, or if its first inhabitants were of African or even possibly Pacific descent. The last thing I want to talk about in relation to Africans making their way to the Americas actually has to do with Columbus himself, and more specifically his third voyage to the Americas. It was recorded by the historian Bartolomé de las Casas that Columbus's sole purpose on this voyage was to test the claims that had made it all the way to King John II of Portugal. These claims described how canoes had been found which set out from the coast of Guinea, which is West Africa, and sailed to the west with merchandise. Or basically, people from West Africa were sailing out west into the Atlantic with valuable things for trade, and King John of Portugal was curious about where these goods were going. Following these directions, Columbus sailed for the west of Africa and discovered the continent of South America. Whether or not these myths of African merchants were true, the land they were supposedly traveling to was real, which, if you ask me, gives at least some credence to these stories. Despite this, there's still been no tangible evidence to back up these claims other than word of mouth from some long dead and lost original sources. Moving away from Africa and the Atlantic Ocean as a whole, we come to East Asia and the Polynesian Pacific. Now, if we again look at the prevailing wind patterns that may have helped Africans reach the east coast of the Americas, the opposite is true in the Pacific, where winds blowing east to west would have impeded explorers' ability to travel east near the equator. But the opposite is true at higher latitudes, where prevailing winds could have helped push explorers towards the Americas. These are collectively known as the westerlies, which blow from the west to the east. These wind patterns result in ocean currents in the Pacific that look pretty similar, forming an ocean gyre which moves water from around Japan all the way to the American west coast. Before we get talking about ancient East Asians traveling to the Americas, I want to give a brief summary of the story of the three Kichis. You see, while serving as crew members on a rice transport ship, 3 Japanese men, Iwakichi, the ship's navigator, Kyukichi, an assistant cook, and Odokichi, another assistant cook actually, and 11 other men encountered a storm in the western Pacific, off the coast of Japan. During the storm, the mast and rudder broke off from the ship, leaving it and its crew stranded in the middle of the Pacific. But because it was a rice transport ship, the men actually had enough food to survive, and over 14 months, the Pacific Ocean Current, now called the Kuroshio Current, took the boat and the surviving crew across the ocean and deposited them in Washington state. By the time they arrived on land, only the 3 Kichis remained, everyone else having died from nutrient deficiencies. There's a lot more to this story too, but for our purposes, this is the first recorded example of a boat being swept from Japan to North America entirely without a source of propulsion or steering. Events like this have been recorded several times afterwards as well, and many scholars find it hard to believe that these events only started to occur after the Columbian discovery. I guess I should stress again that we don't actually have any evidence of this happening prior to colonization of the continent, and all statements about this are entirely circumstantial. If we take another look at the prevailing winds and currents in the Pacific though, we can see the Kuroshio Current is mirrored in the southern hemisphere by the South Pacific Current, which opens up the possibility of an American discovery by the Polynesians as well. Now, it's already well known that the Polynesians were master seafarers and navigators, which might explain why there's possibly the most evidence in favor of contact between the Polynesians and Native Americans. There are numerous examples of this, but my favorite includes the sweet potato, which is known to have originated in Central and South America. But when exploring the Pacific, early Europeans also found them growing throughout Polynesia. Now, most of the islands the Polynesians inhabited were volcanic in origin, meaning they never shared any sort of geological history with America, and therefore the sweet potato must have been brought here by some other means. Some have used this to say that the Polynesians themselves arrived in South America and brought vine clippings back with them to farm, while others have proposed that the vegetable managed to disperse itself by riding ocean currents over many thousands of years. This theory of a Polynesian introduction, however, would help explain too why the Proto-Polynesian word for sweet potato, kumala, is noted to be very similar to those of South American Quechua and Aymara words for the same crop, komar and komara. I should remind you, there are also numerous other similar examples to this one, which include everything from Peruvian mummies being found with sap from a New Guinean tree, all the way to canoes in California resembling both in form and name those built by the Polynesians. Like I said at the beginning though, none of these hypotheses have been proven with large amounts of undisputed evidence. Obviously, someone made it to America before Columbus, as evidenced by all the millions of people in ancient civilizations found here upon first contact. Clearly, these people were the true discoverers of America, as they were the first to establish permanent settlements on the continent, thousands of years before Columbus or Leif Erikson or anyone else. Discovered is a relative term in this video, as I hope you realized instead of writing redundant comments down below. I'm not saying any of these have been legitimized to the point that we need to change our history textbooks. All I'm trying to say is that there are things in this world that should make us question our understanding of American discovery and exploration, and world history as a whole. Regardless of what the answer is, the question who discovered America is still a question I believe is worth asking, and can only help to improve our understanding of history that has long since passed. I hope you agree with me on this one, and judging by the fact that you watched this entire video, I'd say you would. Besides that, let me know of any other questionable examples of people making it to the Americas before Columbus. I find this topic very interesting. If you want to keep seeing videos like this, I'd suggest checking out my Patreon. That's how all these people got their name on here, and that's how I keep this channel running. I should be back next week with another video, so subscribe if you want to see that. Thanks! About 2 million years ago, early humans hadn't figured out farming yet, so they mainly relied on collecting fruits, tree bark, tree roots, and even insects to survive, as did several other hominid species, including one called Australopithecus. But around this time, a change began to happen, not among the humans, but the climate. An ice age was beginning, and for many humans, long portions of the year were marked by cold temperatures and food shortages. To overcome this obstacle, the solution Australopithecus came up with was to eat a higher quantity of lower quality plants like weeds and grasses, while Homo sapiens, that's us, found that in times of scarcity, animal meat and bone marrow could supplement fruits, and actually provided greater amounts of protein and access to different important nutrients that only a few plants could provide. If you look around today, only one of us is still around, as Australopithecus died out around 2 million years ago, and it's thought that their different feeding habits influenced their eventual demise. In this way, eating meat helped save humans from extinction. Ever since then, humans have been hunting and eating animals to satisfy parts of their diet, and eventually figured out that if we captured some of their young and raised them alongside us, we didn't have to put ourselves in danger and could have a reliable source of food. This process of training and breeding animals to coexist with humans is called domestication, and any animal we raise for the purpose of eating or deriving some other value out of, like for their eggs, milk, or leather, is called livestock. And although today many of these are found all over the world, each one had to have come from somewhere specific, and each one has an interesting story behind their domestication. So let's get the big one out of the way first: chickens. The term chicken actually used to mean just the young ones, while the term fowl was used for the whole species. That's why we still call all young birds chicks, even if they aren't chickens. Honestly, I could do a whole video about chickens, so I hope you're ready for this. Modern-day chickens are the domesticated form of what's called the red jungle fowl, a bird that struts along the floor of tropical forests, scratching seeds and other foods out of the soil. In the wild, the red jungle fowl originated over an area stretching from India into China and down into Southeast Asia, making it all the way to Sumatra. And to this day, there are still wild populations of jungle fowl throughout this area. Although out of the red jungle fowl's initial range, the earliest definitive evidence of chicken domestication comes out of Hebei province in China and would have occurred around 7,400 years ago. From China, the domesticated chicken quickly spread east, with evidence of domesticated chickens in India from around 7,000 years ago. By around 5,000 years ago, they made it to Anatolia and into Eastern Europe not long after. Evidence of chickens in the Middle East only go back to 4,000 years, and they only reached Egypt around 3,400 years ago, or by about 1400 BCE. The shocking part about all this, however, is that the chicken had not been domesticated for farming or even consumption yet. Instead, this entire time, or for the first 5,000 years after chickens were first domesticated, they were being used for the sole purpose of cockfighting, both as entertainment as well as gambling. The first evidence we have of people actually farming and eating chickens comes from only 2,300 years ago in the ancient Israeli city of Maresha. It was here that a tremendous collection of over 1,000 chicken bones were found. These bones were mostly from female chickens, so they couldn't have been used for cockfighting. There were many fully mature bones, so they weren't being selectively killed at birth, and most importantly, the bones bear markings from knives, indicating that they were being cooked and cut up. With 19 billion total chickens alive today on Earth, grown solely for their meat, I think it's safe to say we use them more for eating than gambling now. And our domestication of the chicken has made it the most populous bird on the planet, with 2.5 chickens for every human on Earth. Okay, I think I'm about done with chickens. Cows, which also go by the name cattle, are actually older than domesticated chickens, and they can trace their wild heritage back to a beast known as an auroch, which has since gone extinct. But we still know what they look like because they are one of the most common images to have been recorded as cave paintings. Yeah, they look a lot like cows, that's kind of the point. These were an incredibly versatile animal that really only needed grass to survive. Because of this, they basically originated anywhere with grass, and their range spreads all the way from Western Europe through Asia all the way to China. DNA analysis, however, indicates that the domesticated cow we're familiar with today likely originated from just around 80 aurochs near the village of Çanlıurfa in modern-day Turkey, maybe even by a single group of people, which is really crazy if you think about it. Cows that came out of this domestication event are called taurine cows, and sometimes mistakenly called European cows. A second domestication event happened, however, which resulted in Indocene cows, which, if you couldn't tell by the name, happened near the banks of the Indus River in modern-day Pakistan. These look notably different from most cows we're used to, featuring, among other things, a large hump on their back. Instead of cows, these can also be called zebu, and not everyone agrees that they should be considered the same as cows, but at least genetically speaking, they're essentially the same animal. Cows are also thought to be one of the oldest forms of currency, and if we still used them, India would be the richest country on Earth, hosting over 300 million of them, or roughly 30% of the world cow population, and Brazil would be second with 232 million, or 23% of all the cows. And yet, YouTube refuses to pay me in cows, and Patreon doesn't even let me make a choice to receive donations in cows. Pig also used to be the word for a young pig, while the word swine was used for the whole species. Which means someday piglet could come to mean an adult pig, and then we would need to find a new word, probably something like piggle for their babies. The swine as a whole, however, are the domesticated version of the Eurasian boar, which, as the name implies, also kinda had a ginormous range throughout Europe and Asia, but it's thought more anciently they originated out of Southeast Asia around 2 million years ago. However, they were domesticated in more or less the same exact place as cows within the Tigris River basin, likely south-central Turkey as well. Since Turkey seems to be very popular so far, let's talk about turkeys next. I was surprised to find that turkeys actually did get their name from the country Turkey, but maybe not in the way you'd expect. You see, wild turkeys had an original range across North America, nowhere near the country of Turkey, most likely originating in the warm pine forest of Mexico. But upon finding America, Europeans realized just how much they liked them and brought them back to the old world. Quickly, turkeys made their way to the Ottoman Empire, which excelled in the trade of a very similar bird, the guinea fowl. The Turkish people came to breed and further domesticate the bird and began distributing it throughout the Mediterranean and all the way back to Britain. From there, the bird became associated with those who traded the bird, and they became Turkish birds, birds from Turkey, and eventually just turkeys. I guess the Turkish just really love domesticating animals. Moving on to sheep, like all of these, sheep had a more wild ancestor called a mouflon, from which modern domesticated sheep were bred from. These guys looked 1,000 times cooler than modern sheep, and I definitely want to ride one. The original range of mouflons was from the Caucasus into, Anatolia, modern-day Turkey, and down into Iraq and Iran. They were one of the first domesticated animals when, 11,000 years ago, the Mesopotamians domesticated them. Though it's unclear where exactly in Mesopotamia this happened, who are we kidding, it was probably Turkey. Goats are very similar to sheep, so it only makes sense that they come from roughly the same place and were domesticated at roughly the same time. Except domestic goats likely came from the wild Bezoar ibex, which has some serious horns, and actually have the largest horns relative to body size of any animal on Earth. These have a range from the Zagros Mountains into, Turkey and the Caucasus as well. The term to refer to a baby or a young goat is just kid, so this is just a bunch of kids. This phrase comes from England and is actually older than referring to human children as kids, which originated in America during the 1800s. So basically calling a child a kid means you're calling them a baby goat. Horses are probably the most awesome of the animals that we eat, and also help in finally getting us out of Mesopotamia. They likely roamed the Pontic steppe from Ukraine through Russia and all the way into Kazakhstan, and it was here that they were also likely domesticated around 6,000 years ago. The earliest irrefutable evidence of horse domestication comes from sites shared between Russia and Kazakhstan, where the horse carcasses were found buried with chariots, clearly indicating they were being used and had been for some time. A very close relative of the horse is the donkey, which are also called ass, and a female donkey, now called a jinni, was just called a she-ass. I'm telling you all this not because it's important, but because I have to have fun making these videos too. Despite being close relatives to the horse, they originated from the African wild ass, which had a range from Egypt all the way down to the Horn of Africa as far as Somalia. However, this region used to be a lot more grassy, and now their true range is centered around Ethiopia. But this original range explains why the donkey was originally domesticated in a place called Nubia by pastoral people in modern-day Sudan. Camels are kind of difficult because there's really two different camels, the dromedary, what most of us consider as a regular camel, and then the Bactrian camel. Dromedaries, also known as Arabian camels, are just that, originating in Arabia and spilling over a bit into North and East Africa, and it was either here in Arabia or in Somalia that they were first domesticated. Whereas Bactrian camels come from, Bactria, which is roughly this area, mostly in modern-day Afghanistan and Pakistan. Because of their original habitat, it was these types of camels, the Bactrian ones, that were used for the Silk Road. Closely related to camels are llamas and alpacas. Because of their similarities to each other, they're often confused, but they are in fact different animals. The important difference between them is size, as llamas can be up to 6 feet tall, whereas alpacas are smaller, typically only over 4 feet tall. The range of the llama is also bigger, stretching from Ecuador down to Chile and even Argentina, while alpacas can mostly be found within southern Peru and northern Chile. But basically, both can be found within the Andes and are sort of just used as the cows of the Andes Mountains. If that's the case, then the cows of the Himalaya Mountains would be yaks, which are basically cows that grow their own skirts, as they've become adapted for cold and mountainous regions. The most important difference between cows and yaks, however, in my opinion at least, is that while cows moo, yaks grunt. And even their Latin name, Bos grunnius, reflects this, translating into bull grunting. The last two livestock creatures I want to talk about aren't often thought about. Typically, we don't directly eat these, but instead we just use the products they create. The first one is the silkworm. These are the larval stage of the silk moth, which produce, yeah, you guessed it, silk. The wild silk moth has a range starting in northern India and coming all the way up into northern China and even into far eastern Russia. Domestication occurred in China roughly 5,000 years ago, and then the secret of their domestication was closely guarded when outsiders came, and Europeans had to steal silkworms in order to figure it out. It's a very interesting story, but we don't have time for it right now. Lastly, we have the honeybee. Now, some might argue this doesn't count as a domesticated livestock, but they're still an animal that we derive a tremendous amount of value from, both through their honey and wax, but especially through their pollination practices. So I figured I'd include them regardless. Of the 20,000 different bee species that exist on Earth, only 7 produce honey, and it's thought that the first honeybees came from Africa and spread naturally across the rest of Eurasia. And today, the most popular one is called the Western honeybee, or sometimes the European honeybee. Hint hint. And because Europeans had a lot of fun sailing all around the world and meeting a bunch of new people and definitely didn't do anything bad in any of these places, the modern range of the Western honeybee looks like this. Although they likely originated closer to this area, cave paintings in both Spain and France have been found depicting humans collecting honey from beehives. The first evidence of actual domestication comes from Egypt, where tombs have been found with images of beekeeping from around 9,000 years ago. Which is crazy because beekeeping suits wouldn't be around for another 7,500 years. They were only invented in the 1500s, so yeah, for over 7,000 years, people took care of bees with nothing or close to nothing. Which I like honey and all, but overall doesn't seem worth it. That's about it for livestock. Let me know if you'd like to see another video, maybe about our grains, vegetables, or possibly even pets. As always, thank you to my patrons for helping make this video and this channel possible. If you want to get your name up here like these generous people, I got a link coming up for you. Of course, you should subscribe if you like this, and if you haven't yet, maybe you should check out my videos on where spices and fruits came from. I'll be back soon with another one. Thanks. Let's face it, spices are the best part about eating food. They're what go into sauces, seasonings, and directly onto our meals to make us want to eat. The fact that spices are great has been known for millennia now, and has at certain points in history led to tremendous changes in society, economics, and people. After all, Columbus was trying to find a new route to the East Indies to access the spice trade when he accidentally stumbled upon America. That means everything afterwards, the colonization, the destruction of the indigenous population, and even the Atlantic slave trade were all inadvertently caused by the search for spices. Before that, caravans would cross deserts and seas to transport spices from one end of the known world to another. Not only did this drive the exchange of goods and currency, but created cultural interaction and diffusion, leading to the spread of ideas, religions, and technology across the world. Despite the huge role spices have played in human history, few people know about the vital role geography plays in both the growing and usage of spices in foods. Perhaps the most important thing to understand about them is that spices are defenses. Let me explain. So the same way predation of smaller animals by larger ones leads to certain animals developing some crazy defenses, plants are eaten by animals in what's called herbivory, which can lead to plants developing similar defenses over time. Some examples of this include plants growing thorns, high off the ground, and thick skins like bark. But by far the most common form of defense plants use are chemical defenses, usually by storing up a large amount of toxic chemicals in their bodies, so that when eaten by herbivores, it either kills them or at least injures them enough so that they never eat that plant again. So the same way poison dart frogs accumulate poison on their skin to deter predators from eating them, plants will store poisons in their bodies or fruits to deter herbivores. These poisons are our spices. For bigger animals like humans, this poison just tastes interesting, aggressive or different, because we have a much higher tolerance than the smaller organisms that these chemicals target. By now, you might be asking, but they're still toxins, right? So why do we enjoy eating them at all? The answer to this is actually found in the single greatest plant predator on Earth, decomposers. More specifically, bacteria and fungus. Most often, the toxins stored in the bodies of plants are to prevent the growth of these decomposers inside the body of the plant. If it weren't for these chemicals, decomposers could get in and, well, decompose things, killing the plant in the process. So now, think about humans a few thousand years ago. They'd hunt and catch animals, and sometimes massive ones, whose meat would sustain tribes for days or even weeks. But they couldn't simply put their leftovers in the fridge. Without that convenience, bacteria and fungus like mold would quickly grow and make any leftover food rancid. If only there was a chemical designed to kill bacteria and fungus that was so abundant you could metaphorically say it grows on trees. Oh wait, here's this weird red thing that kind of makes my tongue tingle when I eat it, but it does exactly that. So yeah, spices were used to kill any bacteria and such growing on our food in order to prolong the window in which it could be eaten. They'd also help mask any bad flavor the meat had acquired due to rot. This made spices extremely valuable. If you wanted to survive, you had to be able to stomach these toxins. Therefore, whoever was more resilient to the toxins we called spices were more capable of surviving in times of scarce food options. Basically, whoever could handle spicier foods could eat the safest food. In this way, evolution selected towards us not only being spice tolerant, but actually for us to enjoy the flavors of spice because it meant we were eating safe food. But the use of spice didn't happen evenly across all human populations. If you think about it, we put food in refrigerators to make them colder so that they last longer. This has to do with the metabolism rates of bacteria and such, as metabolisms occur at faster rates in warmer temperatures, meaning bacteria can eat and reproduce faster and cause even more damage. Therefore, putting food in a warm environment will shorten the amount of time that it's safe to eat. What this results in is food rotting faster in areas that experience warmer climates, like the tropics. To combat this, a greater quantity and diversity of spices are typically used in tropical and subtropical places to counteract the higher rates of bacterial growth. In colder places, like the temperate regions, the opposite is true. Sometimes, the temperature here can fall below freezing, and food will stay good if you just leave it outside, meaning there's less of a need to season it with spices. It also just so happens that it gets cold right around the same time food gets sparse, and preservation becomes a necessity. Think, in the summer, food is usually plentiful, and therefore there's no real need to preserve food because you can always find more. But in the winter, animals take refuge and all the plants lose their foliage and fruits, so the food people can find has to last longer. What I'm getting at is the only time food needs to be preserved in the temperate areas, the environment does it for us. But in the tropical regions, the dry season will come to make food scarce, but high temperatures persist, making spicing food necessary. This explains why cuisine in, let's say, Britain is disgusting, but food in, let's say, India is amazing. This is also why so many Europeans valued spices so much and sailed everywhere in the world looking for trade routes to access these spices. On the biological side of this, because bacteria and fungi grow faster in warmer conditions, plants around the equator are more likely to store up chemical defenses to dissuade them as well. So not only did people who lived in the tropics have a greater need for spices, they also had a greater and more diverse arsenal of spices to choose from. This has led certain areas on the globe to develop abundant natural spices. Because of this, instead of doing what I did with fruits and go through each fruit individually, I decided this time to go through the hot spots and then catch any spices that don't belong to a certain hot spot at the end. The first important concentration is to be found in India and the rest of Southeast Asia. This area stretches from the subtropical into the tropical and once hosted the largest and oldest rainforest on the planet. Southern India is where basil, turmeric, and black pepper, the most common pepper we use today, comes from. Curry also originated here, but that's actually a combination of several different spices, not just one plant. Further south, it's thought that cinnamon first began in Sri Lanka. To the east, we have where ginger and the licorice plant got their start. And yeah, before you ask, it's the root of the licorice plant that we used to flavor licorice candy. Lastly, for this region, we maybe have the most common spice currently being used in the world: sugar. A lot of people might disagree with this, but if you think about it, it's just another plant-derived substance we use to flavor our food, which is exactly what every other spice is too. Whether or not you consider it a spice though, sugarcane, the plant responsible for 80% of our sugar production, is thought to have come from this region as well. Nearby are what's called the Maluku or Moluccas Islands in Indonesia. However, they used to have a much simpler name, the Spice Islands. From these few small islands, cloves, mace, and nutmeg originated. It was these islands in particular particular that drove the Portuguese and later the Dutch into the East Indies, and it was a trade route to these islands that Columbus was looking for when he set sail in 1492. Then, on the other side of the world, Mexico was also a hub of maybe a lot of people's favorites. It was here that both paprika and vanilla originated. What's strange is that traces of vanillin, the compound that gives vanilla its flavor, has been found in old world tombs dating back thousands of years. Archaeologists found this substance coating the jugs within an untouched Bronze Age tomb in Megiddo, Israel. This indicates there might have been some exchange between the Americas and the old world almost 4,000 years ago. Also, they were using vanilla to flavor their olive oil, which, I don't know, just doesn't sound good. If that isn't enough though, it was also here that the cacao tree, what we use to make chocolate, was also first domesticated, most likely by the Olmec or Mokaya people, though the plant itself likely originated further south in the Amazon region. This plant was so prized that its beans were used as currency throughout several different Mesoamerican cultures. What's funny is that initially this plant wasn't desired for its beans, which is the part we now use to make chocolate, but instead it was the sweet pulp of the plant that was highly valued because it would be fermented and used to make alcohol. Iran is actually where a lot of spices are grown today, as its hot and arid climate replicate those found in places like the Mediterranean and Mexico very well. As for what spices originated here, both cilantro/coriander, yeah they're the same thing, and cumin came from this area. But I saved the most important herb and spice hotspot for last. The Mediterranean region. To start, the most common type of bay leaf comes from this region, though different types can be found across the world. Chamomile also came from this region. Mostly used for tea now, it got its name in English via French, via Latin, via the Greek word chamaimelon, meaning earth apple. Fennel plants aren't too popular, but they're one of the main ingredients in making absinthe. The Greek word for fennel is marathos, and marathon literally translates into field of fennel. So the Greek city of Marathon was originally just built in a field of fennel and named accordingly. Then a battle between the Greeks and Persians happened here, and someone had to run 26 miles to Athens to tell them about it, and that's how we ended up with the marathon race. Lavender also came from the Mediterranean region, which for the longest time went by the Greek name nard, so good call switching it to lavender. Mint has spread across the world, but it's thought to have originated here as well, though it grows best in wetter climates. Primarily, mint is grown near other, more important plants, so its pungent smell keeps other pests away. It's basically only humans that actually like the smell and taste of mint, which is weird because mint is almost exclusively used because we think it smells good. Breath mints, toothpaste, mouthwash, and chewing gum all use the aroma of this leaf, which only exists to keep herbivores from eating it with its awful smell. Actually, I guess that does make sense, because if your breath smells like something that kills bacteria, then your mouth must not have any bacteria, and therefore must be clean. Anyway, mustard plants also got their start in this region. While many might be thinking of the condiment mustard, which is made from the seeds of mustard plants, mustard as a family includes the genus Brassica, which also includes turnips, cabbage, collard greens, kale, cauliflower, broccoli, Brussels sprouts, and canola plants. Yeah, mustards are more important than people realize. Oregano, on the other hand, is known to have originated specifically in Greece, and its name comes from the Greek words oros, meaning mountain, and ganos, meaning joy, to make joy of the mountains, which is where wild oregano first grew. Saffron is one of the most expensive spices by weight, and that's because the part we use as a spice comes from the elongated stigmas, this part of the saffron flower, which usually only yield a couple per flower. They were specially bred on the island of Crete during the Bronze Age to be like this. From here, it spread to become popular in foods and medicines. While rosemary, sage, and thyme also come from this general region. They're pretty regular spices. I couldn't find anything cool or specific to say about them though. And that wraps up all the major hotspots for spices. Next, we have the spices that appeared all on their own. Allspice, which has been described as sort of tasting like cinnamon, nutmeg, and cloves all together, is also known by another name, Jamaican pimenta. So yeah, no surprise, allspice got its start on the island of Jamaica in the Caribbean. Cayenne peppers are the classic red pepper most people probably think about when thinking of spicy peppers. These actually come from the French Guiana in South America, specifically from the Cayenne region. Funny how that worked out. The name cayenne originally comes from the native Tupi word guiña, which also just means pepper, so cayenne pepper literally translates into pepper pepper. Garlic, in my opinion, is just the best, and comes from Central Asia, where Kazakhstan, Kyrgyzstan, and the Chinese Tian Shan Mountains meet. Then we have jasmine, which is actually a genus containing over 200 individual species. Being so numerous, it's hard to track just exactly where they started, but it's thought that southern China is where they came from. Sassafras is really the only spice I have on this list that comes from a more temperate, wet climate, originating in the east coast of North America, roughly from Ontario, Canada to Florida in the United States. It's the root of this tree that was used to flavor root beer, hence the name root beer. And lastly, we have the spice melange, which we all know is native to and only grows on the desert planet of Arrakis. Thanks for watching, I hope you enjoyed this, and if you did, maybe consider liking and subscribing. If you'd like to support me and this channel, you can throw a little spice my way through my Patreon, like these guys. These donations really help me continue making these videos, so thank you to everyone who has already donated. Other than that, check out my Twitter for updates, and I'll be back soon with another video. Thanks. The Earth is in trouble. Well, actually, no, that's inaccurate. Really, the Earth is fine. It's humans that are in trouble. As our society expands, so does our dependence on fossil fuels. And aside from the fact that using these increases the heat absorption in the atmosphere, causing global climate to shift, there may actually be an even more dangerous aspect to relying on things like oil, coal, and natural gas as a fuel source. And that is, fossil fuels are limited, and one day they will run out. Not if, but when this happens, all that we've built will need a new source of energy, and if we can't find one, it could all go away. So whether it's in 5 or 500 or even 5,000 years, whether it's to save the planet or just to save ourselves, we're going to need to find an alternative to fossil fuels eventually. There's no argument here. But some of us depend on fossil fuels more than others, and responsibility on this issue isn't shared evenly throughout the human population. If we look at the top 10 highest energy consuming countries per capita, we can see that Iceland tops the charts with over 50,000 kilowatt hours per person each year. For some perspective, the global average is only 2,600 per person, and the average for someone in the United States is 12,000. Of course, high energy usage isn't necessarily a bad thing, and Iceland actually serves as a model for the right way to produce and consume energy. This is because 85% of the country's energy demand is actually met through renewable resources like hydropower and geothermal energy. But really, nearly 100% of Iceland's electricity comes from these renewable resources, and the only fossil fuel usage comes from things like cars, which aren't so easily converted to electric. Sadly, but unsurprisingly, Iceland's contribution to ending fossil fuel consumption isn't enough to save the world, and it's going to take a lot more countries making similar scale efforts to accomplish this. Probably the worst example of energy consumption comes from, yeah, you guessed it, the United States. In total, we use over 3.9 million gigawatt hours per year, second in the world only behind, you can probably guess this too, China. What this means is that with a population of only 324 million people, America uses more energy than all of India, which has a population of almost 1.3 billion. Or another way to say that is, even with 1 billion more people, India uses less than half the energy the US does. In total, the United States accounts for 18% of the world's total energy consumption, while containing only 4.4% of its population. Again, this wouldn't be a problem if the United States was like Iceland and received this energy from clean, renewable resources. But if we look at a breakdown of where the country receives its energy from, we can see this is definitely not the case, as renewables only make up roughly 11% of the country's needs. Instead, the US mainly relies on petroleum at 37%, natural gas at 29%, and coal at 14%, all of which are fossil fuels. And because I can already feel people asking in the comments, what's left is from nuclear energy. You're welcome. So yeah, not the most sustainable system so far. Unfortunately, we can't just copy Iceland's homework and make their strategy work for us. Well, maybe in some places we can actually. We have plenty of rivers for damming, and Yellowstone is one of the most geothermically active places on the planet. But these approaches have their own environmental drawbacks, namely destroying river ecosystems and intruding on national parks. Of course, these aren't the only two sustainable options, and specifically, in recent years, the United States has been seeing increasing interest and investment into solar energy. But what would it take for the United States to become like Iceland? Or even better, what would it take to go 100% solar? So I already said that the United States uses an estimated 3.9 million gigawatt hours per year, which for simplicity's sake and also because that number is expected to grow, we'll just make into 4 million per year. With current technology, it's possible to produce 1 gigawatt hour over 2.8 acres of land using solar panels. This figure doesn't account for things like roads and other infrastructure that would need to be built to accommodate the solar arrays, so I'm just going to round this number up to 3 acres per every gigawatt hour. So to generate 4 million gigawatt hours, about 12 million acres of land will be required. This might sound like a lot, but the United States covers an area of over 2.4 billion acres, which means this solar farm would amount to only 0.5, half of 1% of the country's total surface area. Yeah, acres are a lot smaller than I realized. If all of this were concentrated into a single array, it would look something like this. In terms of size, this would be just a little bigger than Maryland and just a little smaller than West Virginia, or roughly the same size as Vermont and New Hampshire combined. If this were made into its own state, it would be the 10th smallest in the country. If this still seems like a lot though, I'll give you some more figures. According to the US Bureau of Land Management, over 25 million acres of land in the US alone are leased by oil and gas companies. That's over twice the space needed for solar panels to supply 100% of our energy needs, while oil and gas together only provide the country with 66% of its energy demand. But okay, let's say we wanted to keep these lands extracting fossil fuels so that we could sell them and help pay for the whole project. Even still, every year the US federal government offers up leases on federal land to oil and gas companies in the form of auctions. In 2017, the amount of land offered up reached nearly 12 million acres, almost the exact amount of space needed for our solar array. Of this nearly 12 million acres of already federally owned, unproductive land, less than 800,000 acres of it received a bid. That means there's still at least 11 million acres still open for use that the government would have to spend absolutely no money to acquire. One last comparison I'd like to make has to do with corn. In the United States, over 21 million acres are used to grow corn with the specific purpose of converting it into ethanol to be used as a gasoline substitute. In fact, corn grown for ethanol production is actually the second largest use of corn in the country, only behind growing for livestock feed, and accounts for 27% of all the corn we grow. This 21 million acres is, again, nearly twice the amount of space that would be required for our solar array, which could, again, power the entire country and not just a small fraction of it. What I'm trying to get across is that dedicating 12 million acres to solar energy production is not only relatively small in scale, it's actually much less than what we're already using for energy production in the United States, and is actually a much more efficient use of our land. Okay, so knowing that, next we need to ask, how would this be implemented? To start, although it would be really cool, we likely wouldn't build a single huge solar farm that'd be visible from space, but instead split it up into many smaller fields across the country, and we would do this for several reasons. The first being that a single moderately sized cloud could cover this entire array if it was all kept together, effectively cutting all power for the country. Second, transporting energy always results in energy loss through the heating of electrical cables, and the further you need to transport it, the more energy that is lost. So it'd be better to keep these solar fields closer to multiple population centers, therefore reducing overall waste. That being said, it would not make sense to spread solar panels evenly across the United States either, as many areas don't receive the proper amount of sunlight per year to make them effective. Instead, it would be best to concentrate our solar fields into specific high sunlight receiving regions. If we look at this map of the country, which shows the average daily solar energy reaching the surface, we can see several things. First, the entire East Coast really isn't a viable option if we're looking to maximize the output of our solar panels. Meanwhile, the American Southwest looks to be the best location for a massive array of solar farms. This is the result of two main factors. One being the further south you get means there's more sunlight hours and less seasonality over the course of a year. But perhaps more importantly, if we look at a map of precipitation in the United States, we can see that this region is arid, receiving the lowest amounts of rainfall and therefore cloud cover anywhere in the country. Together, this means this region receives more direct sunlight than anywhere else in the US. And in fact, in places like the Mojave Desert, which lies within this region, a number of solar farms have already been constructed. These two factors make this land the best in the country for solar production, but one more aspect really makes it perfect, and for that we need one more map. This one shows the land owned by the federal government in the US. Here you can see a large amount of this land within our desired range is already owned by the government, which means money would not need to be spent to acquire any land here. In short, not only does this project require far less land than we're already using for energy production, but the land that's most suited for solar energy production is also already in the hands of the government and for the most part lying vacant. Since we know that land area and ownership is not the issue now, we have to ask what is, because none of this matters if it can't be implemented. The primary barrier to this project is upfront cost. Solar panels aren't the cheapest thing, and actually they're pretty dang expensive. Estimates for the total cost of implementing such a large-scale solar operation vary quite a lot due to different factors being taken into consideration, but everyone seems to agree that this project would cost far beyond what the country is capable of right now. The most moderate figure I've found, so between the biggest and smallest numbers given, was $24 trillion. To put that into perspective, the entire GDP of the United States is only $19 trillion. So yeah, this wouldn't be the cheapest project in the world. If you need something to compare this to, the International Space Station cost only around $150 billion and represents a collaboration between 14 countries. Even still, this solar panel project would cost over 160 times that. But the United States has completed even more expensive construction projects than this, all on their own. The interstate highway system is often considered the most expensive modern construction project ever completed, coming in at a price of $459 billion, or 3 times more expensive than the International Space Station. But still, this is nowhere near our solar panel project. Even still, the country has spent more on a singular purpose before. Specifically, in recent memory, the Iraq War came in at an estimated cost of $2.4 trillion to the United States. We're getting closer now, we're at least in the trillions. So another way to put this is that a 100% solar power grid would cost the United States 10 Iraq wars. But we'd also gain far more from this project than any war in history could offer. Yet there are still even larger projects to compare this to. The closest comparison I can make has to do with a project that's actually underway right now, and that's China's Belt and Road Initiative, which is a mega project with the goal of creating infrastructure corridors throughout Asia, Europe, and Africa to allow for greater degrees of trade and exchange across these places. The project includes the construction of new roads, bridges, freight lines, seaports, and even potentially a unified electrical grid across a total of 68 different countries. This project is by far the largest in human history and has come with price estimates anywhere between $4 and $8 trillion. This is the best I could do to put this project into perspective, as it would still be at best 3 times more expensive than this. So yeah, this would still be a massive undertaking, like the biggest in history massive, but maybe not for much longer. Prices of photovoltaic cells and other related technologies have been steadily decreasing, while efficiency and energy storage potential of batteries has been improving. Whether or not a 100% solar United States is possible really depends on how much research we choose to put into renewable technologies. Of course, solar energy isn't the only source of renewable energy, and perhaps not even the best for our purposes. In reality, we definitely use other forms like wind, hydro, and geothermal to supplement solar. By having a diverse energy network, it makes the system overall more resilient in the case of something going wrong. Just like having multiple sources of income helps give certain people freedom to create content. Yes, it's the Patreon part of the video, I'm sorry. I'd just like to say maybe a few of you have noticed my channel has experienced some pretty spectacular growth recently. 2 weeks ago, I celebrated reaching 10,000 subscribers, and now I just celebrated reaching 100,000. So first, I'd just like to welcome all my new patrons and subscribers. It's really great to have you all here. But also, the channel has started to get big enough for me to do sponsorships, but to be honest, I really don't like the thought of doing those. I'd much rather keep this channel running solely off donations and ad revenue. So if you'd like to help me in that goal, my Patreon link should be somewhere on screen. Other than that, I hope you enjoyed, and if you did, maybe, I don't know, subscribe if you'd like to continue seeing videos like this. Thanks. Plants. It was around 700 million years ago that plants first climbed out of the oceans and made their way onto dry land. After this, what was once a barren and rocky wasteland changed into a lush and thriving world brimming with new types of life. With their roots, the plants could take up nutrients never before used, and with the energy of the sun, create a noxious gas known as oxygen. And this changed everything. With oxygen in the atmosphere, the average surface temperature of the Earth decreased, and animals were at last able to support the growth of bones, grow larger than ever before, and diversify in a million different directions. In this way, plants paved the way for terrestrial life on Earth, and without them, the planet would still be a blue and brown marble instead of the blue and green marble of today. The impacts plants have had on the world cannot be understated, and virtually everything we need to survive comes from plants. Most of our food, plants, or fed by plants. Clothes, mostly cotton, which if you didn't know, is a plant. Our houses are made from wood, which comes from trees, and yeah, those are plants. Even natural gas, oil, and coal, our energy, comes from ancient mats of dead plants. But out of all the plant species that have ever existed, perhaps no plant on Earth has had more impact on life and the climate here than this fern. This plant is known as Azolla, and it's responsible for the climate we experience today. Azolla is an aquatic fern, and unlike most other types of fern, and we'll get into how that is later. You might know it better by one of its nicknames, including fairy moss, duckweed fern, water fern, and mosquito fern. It's quite small, with each plant usually only a couple centimeters in size. But around 49 million years ago, this single plant managed to change the climate of the Earth to the one we live in now. So how did such a small, seemingly unimpressive plant have such a big impact on the Earth's climate? To understand this, we need to go back 49 million years ago to the Eocene epoch. At this time, there were three main conditions which allowed Azolla to have such a huge effect on the world climate, and without these, the world would have been very different today. The first condition was Earth's climate during the Eocene. At this time, the Earth was hot. Earth today has an average temperature of around 16 degrees, while Earth during the Eocene had an average temperature of nearly 30 degrees. As a result, apart from a few deserts, the entire planet was covered in jungle and rainforests, like the one we find only near the equator today. That's including the North and South Poles, where absolutely no ice was to be found. Instead, fossils for palm trees have been found as far north as Alaska, and remains of subtropical plants have been uncovered under the ice of Antarctica. There was also little seasonality, meaning temperatures remained roughly constant throughout the year, and things like winter, spring, summer, and autumn didn't really exist back then. It's like in the movies when planets are just ice planets or desert planets. Earth was a jungle planet. And this meant plants had widely available water throughout the year, and their growing season never ended. The second important condition went hand in hand with the climate, and that was the atmosphere. The reason for these warm temperatures was simple: greenhouse gases, namely carbon dioxide and methane. Estimates for CO2 in the atmosphere at this time go as high as 900 parts per million, which is more than double what it is today. What this means is that as the rays from the sun came down to Earth, there were more energy-absorbing molecules in the atmosphere to capture this energy and store it as heat, rather than allowing it to radiate back into space. In addition to the added carbon dioxide and methane, there were also greater levels of water vapor in the atmosphere, which is even better than carbon dioxide and methane at absorbing energy from infrared radiation. What this did was create a feedback loop, one where warm temperatures caused greater amounts of evaporation and evapotranspiration, leading to an atmosphere containing more water vapor, which in turn led to higher temperatures. This not only created fantastic conditions for plant growth by making the planet warmer, but also gave them more materials to obtain energy with, because plants used carbon dioxide to harvest energy through photosynthesis, and with much more of it in the air, plants had an abundance of resources to support growth and reproduction at this time. The third and last condition which caused Azolla's bloom was plate tectonics. 49 million years ago, the continents were in different places than they are now, and for Azolla, the most important difference was here, in the Arctic Ocean at the North Pole. Today, the Arctic Ocean is a fairly open body of water, with many channels for water to flow in and out. But 49 million years ago, the Arctic Ocean looked more like this. Apart from being much smaller, there was only one shallow channel for water from the Arctic to pass through, and it was cut off entirely from the Pacific Ocean. What this meant is that the mixing of water by deep water currents like the Gulf Stream did not occur, and water was basically trapped in the Arctic Ocean, similar to the water in the Black Sea today. And as I mentioned before, the high temperatures present throughout the planet led to high evaporation rates. As the water here evaporated, what was left were the salts, and this in turn increased the density of the remaining water. And because there was little interchange between the oceans, this pool of very salty, very heavy water remained captured in the Arctic Ocean, unable to escape for a very long time. The only source of fresh water to balance out the salt came from rivers draining from the surrounding lands. But because the ocean water was so dense, the much lighter fresh water didn't really mix with it. Instead, this river water created a layer of its own, suspended above the more saline ocean water. This is called a nepheloid layer, and they're fairly rare, with the biggest one that exists today being in the Gulf of Mexico in this general area. This layer wasn't particularly deep, only a couple centimeters at most, but that's all Azolla needed to thrive. Moreover, because this nepheloid layer was made by river water, it was very rich in mineral nutrients such as phosphorus and potassium, which created the optimal conditions for plant growth. Under these conditions, the circumstances were perfect for Azolla to bloom in high quantities, and the Arctic Ocean became a green carpet indistinguishable from the land. And for 800,000 years, an area of 4 million square kilometers was covered by only Azolla. Now, if this had been any other plant, perhaps the climate would not have changed so drastically. But I said earlier, Azolla isn't like most other ferns, and in fact, it's been deemed a superplant. In a single year, just 1 acre of Azolla can bring down from the atmosphere 1 metric ton of inert nitrogen, as well as 6 metric tons of carbon dioxide. This is important also because plants need nitrogen to produce energy and create new plant cells. And while most plants depend on fungi or bacteria in the soil to produce fixed nitrogen, Azolla has factories of its own to take nitrogen from the atmosphere and fix it into usable compounds, so its growth is not limited by nitrogen availability in the soil either. To make things even better, Azolla is also an extremely productive plant. In today's climate, it's capable of doubling its biomass in only 3 to 10 days. But at the North Pole, where this was growing at the time, certain times of year would receive 24 hours of daylight. With this added sunlight and the high availability of nutrients, it's been predicted that Azolla would be able to double its biomass in just 2 days. Basically, Azolla was unstoppable at this time, and I'll remind you, these conditions existed for 800,000 years. But these Azolla blooms aren't enough to change the climate. You see, in a bloom, the Azolla would take in a great deal of carbon dioxide, but normally, once plants die, they decompose and release this carbon dioxide back into the atmosphere, so no real change occurs. But when the Azolla died, it would drift down into the heavier, more salty waters below, and these waters are what's referred to as anoxic waters, basically meaning there's no oxygen down there, due to the layering of the ocean I described earlier. In this oxygen-depleted environment, little to no decomposers could survive, and the Azolla just sat there at the bottom of the Arctic Ocean, slowly building up, unable to return the carbon dioxide to the atmosphere. And because the only water entering this area was from rivers rich in sediments, the dead Azolla layers would be buried so that once the ocean opened back up, they still wouldn't be decomposed. This is how fossil fuels are formed, by the way, and when people talk about oil in the Arctic Ocean, it's because of this process of sequestration. So, as Azolla piled up, all the energy-absorbing carbon dioxide that was once in the atmosphere became trapped within the Earth, and all that was left was nitrogen and oxygen, which aren't nearly as good at absorbing energy. So when the sun's rays struck Earth, much more of it was allowed to radiate away. With less energy stored in the Earth's atmosphere, the planet began to cool, basically global warming in reverse. As this process continued, for perhaps the first time in Earth's history, ice was to be found at both the North and South Poles, and the average temperature of the Arctic Ocean went from a balmy 13 degrees Celsius to a frigid -9 degrees Celsius. This change also led to the Earth's climate being less stable, which resulted in temperatures more dependent on what time of year it was, or in other words, seasons. The jungles of Antarctica became barren ice, and the palm trees of Alaska faded into harsh tundra. And over the course of 2 million years, the planet entered what is known as an ice house Earth, which is the climate we live in today, and the opposite of a warm, greenhouse Earth. It should be noted that other factors were of course at play here, and a system as complex as the Earth's climate can't be wholly swayed by just one factor. But Azolla did play a huge role in the shifting of the planet's climate, so much so in fact that this whole change is called the Azolla event. I think Azolla should serve as a reminder to us that something so small and seemingly harmless is capable of changing the climate of the entire planet. To all those people who think there's no way humans could affect the Earth's climate, they should see the Azolla event as evidence and a warning. And to all the people who say who cares, the world used to be a lot warmer and sounded nice, just think about where Azolla is now. It once covered 4 million square kilometers of the surface of the Earth, but then it changed the climate to the point where it was no longer able to survive outside of the tropics. We might be thriving now, like Azolla once was, but if we change the climate so much to the point where the planet is no longer habitable for most of us, our population could be severely reduced as well, and we could be relegated to a much smaller role in the world. What I'm trying to say is this is a metaphor. We should learn from this and try to act smarter than a plant by trying to reverse and stop the damage we've done to the atmosphere and environment. Azolla might still be around today, but who knows if we'll be able to keep up with the changing climate. Okay, that's enough preaching from me for one video. I hope you guys enjoyed this video. It was really fun and interesting to make. Please subscribe to my channel if you liked this video and if you'd like to see more in the future. Thanks! Rivers. They are some of the most important natural features on our planet. Wherever they flow, they create a sprawling habitat and diverse ecosystem. For humans, they bring fresh water from distant lands, rich with sediments to make soils fertile, and provide an artery of transportation throughout a land. It's for these reasons and more that many of the first civilizations in history, including Egypt, Mesopotamia, the Indus Valley Civilization, and China, all formed around rivers. With the Egyptians settled around the Nile, the Mesopotamians around the Tigris and Euphrates, the Indus Valley founded, of course, around the Indus River, and the Chinese established themselves among the Yellow and Yangtze rivers. And all these civilizations flourished as a result, and even today, rivers play an important role in determining where people live and where cities form. It's no coincidence that most major cities and highly developed areas exist with a river nearby. You can even see some rivers at night from space, solely because of the urban landscapes surrounding them. But with rivers playing such a vital role in the environment and the history of mankind, it's only natural to wonder which of these is the greatest of them all. In short, what's the longest river on Earth? It seems like a pretty simple question. Just find where a river begins and where a river ends and measure the distance. But in fact, this is a lot more complicated than you think. So before we get into answering the question, let's take a look at some of the problems in measuring a river's length. Okay, take these two rivers, River A and River B. Which one is longer? If you measure simply from the beginning to the end, River B is clearly the longer river. But a lot of people don't like this standard because it's misleading for many practical purposes. Say if you were a boat that had to travel up River A, you would need to travel much further than just the distance from the end to the beginning. It's for this reason that in most practical purposes, a river's length is defined by its path and not by the distance from beginning to end. And when measuring the length based on the path of the river, River A is clearly the longer route. The next problem is what scale do we use to measure the river with? Suppose this distance is 100 kilometers. Let's try to measure River A with it. As you can see, this doesn't stay very close to the path of the river, and we end up with a measurement of 8 segments, making the river 800 kilometers long. Now let's try the same thing with units half the length, 50 kilometers. We end up with 19 units, which equals 950 kilometers. That's over 150 kilometers in difference. This is similar to something called the coast paradox, where it's impossible to measure irregular coastlines because the smaller your unit of measurement is, the larger your number gets, indefinitely. To fix this, we must use an arbitrary unit of length and accept that we cannot be 100% accurate, but close enough. The last problem with measuring the length of a river is that this figure changes over time. As you can see in this time lapse over decades, the river erodes its surroundings and bends and breaks. As the river folds, it becomes longer, and once it finishes this cycle, the river is shortened again. So the length of a river can never be set in stone, and over time, figures will change. Okay, now that we're aware of all those problems, the answer should be just a quick Google search away. However, when looking for the answer, you'll find that many sources actually disagree on the world's longest river, with a dispute mainly between the Nile or the Amazon. According to the Guinness Book of World Records, the Nile is the longest, while the World Atlas supports the Amazon being the longest. On Wikipedia's list of longest rivers, it has the Amazon as the longest. But then if you go to the Wikipedia page for the Amazon, it describes it as either the first or second longest river, whereas if you go to the Wikipedia page for the Nile, it will tell you that it's the longest. So let's take a look at both the Amazon and the Nile and try to see why we can't get a straightforward answer. And to start, we'll look at the Amazon. This river is massive in every way possible. By volume, the Amazon puts out roughly 209,000 cubic meters of water every second into the Atlantic Ocean. For some context on how much that is, it's roughly the volume of Grand Central Station in New York every second. That's more water than the Nile, Congo, Ganges, Yangtze, Lena, St. Lawrence, Mississippi, and Mekong rivers combined, with plenty of room to spare. In fact, water from the Amazon makes up around 20% of all the water in all the rivers in the world. Its drainage basin is also the biggest in the world at 7 million square kilometers. That's roughly the area of 4 Alaskas or 10 Texases draining into a single river. Well, actually, many hundreds, possibly thousands of rivers actually. In terms of volume, the Amazon far outweighs the Nile and any other river in the world for that matter. But what about its length? Well, the mouth of the river is easy enough to spot, right here. Now all that needs to be done is find the furthest source of water from this point. But that's easier said than done when you're dealing with this many tributary rivers. For nearly a century, the Apurimac River was thought to have been the furthest tributary to the Amazon, and was believed to be until as recently as 2014, when 2 American scientists ventured deep into Peru on kayaks to study a nearby river, the Rio Montaro, and found it to be almost 80 kilometers longer than the nearby Apurimac. From its start at the Cordillera Rumi Cruz, the Rio Montaro runs for around 700 kilometers until it joins with the Apurimac. From there, the 2 rivers form the Ain River, which flows for another 300 kilometers until it joins the Parin River to make the Tambo River, which shortly after joins the Urubamba River to make the Ucayali River. This river, by the way, is the one from the satellite time-lapse shown earlier. From the Ucayali, it's another 1,600 kilometers until it reaches the Marañón River, and this is where it officially becomes the Amazon River and travels for another 3,000 kilometers to the ocean. This trip from the Rio Montaro to the ocean following the path of the river has only been made 3 times, the first time being by the Americans who discovered it, and then by 2 other groups after the news broke. And in total, this puts the Amazon at 6,992 kilometers long. Amazingly, this is roughly the same length as the Great Wall of China. However, if we measured from this point straight to the mouth of the river without taking the path into account, it would roughly be only 3,000 kilometers, less than half the distance of the actual river. Okay, so that wasn't too bad. Now, onto the Nile. And this is where things start getting tricky. The question of the source of the Nile has been around for thousands of years and remains unanswered to this day. The ancient Egyptians were the first to send expeditions with hopes of finding the Nile's source, and since then, many attempts throughout history have been made to find the source of the Nile, with each one only adding more confusion and disagreement into the mix. So let's start at the beginning, and by that I mean the end. Here's the Nile's delta, where it pours into the Mediterranean Sea. This land has served as some of the longest and most important farmland in the history of the world, and it managed to feed all of the Egyptian Empire, as well as several others, and it was even called the breadbasket of the Roman Empire. Today, nearly all of Egypt's 96 million inhabitants live by the shores of the Nile, and it's some of the most densely populated land on planet Earth. However, despite its size and notable agricultural importance, and the 3rd largest drainage basin in the world, the Nile's discharge is only around 2,800 cubic meters. Compared to the Amazon, that's only 1/75th the volume. In other words, that's way less. Starting from the delta, it's around 2,400 kilometers before the river splits in any notable way. But here, the Nile divides into the Blue Nile and the White Nile. The Blue Nile flows off for another 1,400 kilometers into the Ethiopian highlands until it reaches Lake Tana. This is where the Nile receives 90% of its water and 96% of its sediments. However, these only come during the rainy seasons in Ethiopia, and this source will occasionally dry up completely in the dry winter season. So this is not the source which keeps the Nile flowing throughout the year. So while the main source of the Nile is quite easy to define and measure, there's still the problematic White Nile, which supplies water year-round, and this is where things get interesting, if they haven't already. After the White Nile splits from the Blue Nile, it continues further south until it reaches a vast wetland region known as the Sud, which is very important to understand the history of the Nile exploration. The Sud derives its name from the Arabic word Sud, which translates roughly to barrier, and it certainly is. This is one of the largest swamps on Earth, and some of the toughest terrain to travel through. This is one major reason why the source of the Nile remained unreachable to early explorers. In 61 AD, the Roman Emperor Nero commanded a legion of soldiers to follow the White Nile to its source, but they were unable to make it through the Sud and had to turn back. This swamp is so impenetrable, in fact, that even more recent expeditions have had difficulty making it through, and to avoid trudging through the Sud, explorers now will usually take a route from the east coast of Africa to the end of the Sud instead of going through. But now we have satellites and airplanes, so that's not really a concern. Through the Sud, the White Nile continues into Lake Victoria, the biggest lake in Africa. And that should be it. The source of the Nile, furthest from the mouth, is right here, right? Well, not really. So Lake Victoria becomes the Nile here, so that's the first place people think of pegging the source of the Nile to be. But then some people say it should be the back of the lake, the furthest point from the Nile technically. But then other people try to compromise and put it at the geographic center of the lake. But no matter where in Lake Victoria they say it is, they're still wrong. You see, Lake Victoria is fed by rivers itself, and therefore the source of the Nile isn't just the lake, it's these rivers which feed the lake. Among these rivers, the Kajira River has been identified as the longest feeding into Lake Victoria, so it gets added to the length of the Nile as well. Just a quick note before we continue, there's also a disagreement if a river's length through a lake should be measured based on the length of the coast between the Nile and the Kajira, or the shortest distance between the two rivers. Measuring the coast would add significant kilometers to the length of the Nile, compared to straight to the Kajira. So it's unclear from here on out, and really depends on what people want to count as the length of the river. But following the Kajira for roughly 400 kilometers, we'll find its two longest tributaries to be the Ravyaranza, which has its sources in the Bururi province in Burundi, and the Nyabarongo, which has its source roughly here, somewhere in the Nyungwe forest of Rwanda. However, there's no consensus on which of these sources of the Kajira River is most remote, and due to the rugged landscape encompassing these areas, it's difficult for explorers to reach them even now. As a result, despite all of our technology and fancy satellites, the most remote source of the Nile still remains a mystery to this day, unless you just want to call it Lake Tana or Lake Victoria. But given the most recent data, measurements of the path of the Nile come in at around 6,853 kilometers long. So even after all that, the Nile comes in second place to the Amazon. Way to go. But wait, the group of researchers who came up with these figures for the Amazon and Nile were from the Brazilian Institute of Geography and Statistics, and no consensus has been arrived at on whether the methods used to reach these numbers were legitimate or biased. So there, the answer to this video is no one really knows, and it all sort of depends on what your opinion of the definition of a river is. Thanks for watching. I hope you enjoyed learning about these two massive rivers, and if you did, please consider liking and subscribing to the channel. It really helps. And maybe check out my other videos too. Thanks! Europe. Today it's densely populated, accommodating a population of more than 743 million. With so many people on Earth's second smallest continent, nearly every square kilometer of land must be put to good use with no exceptions. But what if I told you there was a massive piece missing from it? You'd probably say we have satellites, so there's no way we could have missed that. But it's true. And no, I'm not talking about some little island somewhere. I'm talking about a landmass roughly the size of Great Britain, which was once as densely populated as the rest of Europe, but that's now completely missing from the map. Here's a picture of modern-day Europe. And here's what it looked like roughly 8,000 years ago, minus the glaciers. You might notice the most change happens right here in the North Sea. Here it is again, today and 8,000 years ago. Here's a closer map with modern-day borders drawn in, so you can really see the difference. You can see this area that was once the North Sea is now almost entirely land. This is called Doggerland, and all evidence indicates that it was once a fertile and populated lowland region. In fact, it has been predicted that Doggerland might have been the richest hunting area in all of Europe during the Mesolithic period, and could have attracted huge numbers of people to it. Many prehistoric tools, weapons, and even man-made structures have been discovered in the lands beneath the water. Fishermen here have even discovered prehistoric skeletons of mammoths, rhinoceros, and lions. Studying the contours of the ocean floor here also revealed many lake beds and river valleys. In fact, roughly 10,000 miles of river channels have been revealed through the use of seismic surveys. It was even found that several important rivers in Europe today, including the Thames, Rhine, Seine, Meuse, and Scheldt, once all joined together to form a single impressive river which ran through where the English Channel is today. Okay, so by now you must be asking, what happened to Doggerland? As many of you might have guessed, cause number one of the disappearance of Doggerland was glacial melt. As the last ice age came to a close, glaciers receded and all that water had to go somewhere, and sea levels rose by an estimated 120 meters as a result. But this wasn't enough to fully submerge Doggerland, and actually a fair amount of land still remained after the sea levels rose to where they are today. The second cause is a process known as isostatic rebounding, which is exactly what it sounds like. Well, what does it sound like, you might ask? In short, during the ice ages, the glaciers to the north of Doggerland weighed so much on the crust they actually pushed the crust down into the mantle and hoisted the surrounding areas further up, like a seesaw, but on a massive scale. Once this ice started melting, this process began to reverse, and the elevation of all of Doggerland actually decreased, while the elevation of the area that had previously been under ice increased until everything was back to normal. Even greater portions of Doggerland were lost as this process took its toll on the land. This process of isostatic rebounding is still happening today, mostly in Canada, Norway, and Antarctica, even thousands of years after the ice ages ended, and will likely continue for a few thousand more years. But even after all this had occurred, an island approximately the size of Denmark remained in the North Sea, and this is what's now called Dogger Bank, a very shallow portion of the North Sea, and is where Doggerland got its name from. But that's no longer there either, so what happened to Dogger Bank? This is where it starts getting speculative. Cause 3, well, it's more of a recent hypothesis. It suggested that the final event which caused the total submersion of Doggerland was a mega tsunami. And yes, that's the technical term for it. You see, just a couple thousand miles away, off the coast of Norway, around 6200 BCE, there was a series of 3 massive underwater landslides, collectively called the Storegga Slide, most likely caused by an earthquake nearby. This event created one of the largest tsunamis known to man, and sediments from this tsunami have been found all over the North Atlantic region. Fossils found in the sediment layer created by this event roughly match the time that Doggerland became inundated with water. This is also thought to have been the event which separated Great Britain from continental Europe for good. But if it weren't for that random disaster, Europe could have possibly been home to another small region or even a whole country. Now, if you're thinking this all sounds like the setup for a real-world Atlantis, you're not alone. It has been speculated that this land could have been the origin for such an idea. However, for the most part, the influx of water would have been gradual to the people living there, and would have given them plenty of time to escape to the surrounding regions. This also may explain why northwestern Europe was more densely populated than it should have been at this time. Well, except for those people who might have stuck it out to the end, because I'll remind you, there was a mega tsunami that washed away significant portions of land. What I'm saying is, if you had to ask me where I thought the sunken city of Atlantis might be, I'd probably say somewhere on Dogger Bank in the North Sea. So the next thing you might be asking is what Doggerland would be like today if it still existed. And well, first off, it probably wouldn't be called Doggerland, as it only got that name from Dogger Bank, which got its name from the old Dutch word for fishing boat, dogger, which I'm probably mispronouncing. Dogger? Doger? Dozier? And I doubt there'd be much cod fishing there if it was still land. Trying to guess much more about the modern Doggerland is difficult, but I'll try anyway. I'm also going to keep calling it Doggerland, even though I just pointed out that's not what it would be called, probably. I'm just trying to keep things simple, okay? So first, Doggerland would most likely be a very wealthy nation, as it lies over substantial oil and natural gas reserves that make surrounding countries billions of dollars annually. Ironically, however, Doggerland would likely also be a huge proponent of green and renewable energy due to its low-lying geography and vulnerability to widespread flooding. Doggerland was also, as I mentioned before, predicted to be a fertile land with many rivers, and would most likely have served an intense agricultural purpose. The spot where several major European rivers met and flowed into the ocean would have likely been an extremely strategic spot, and likely would have become the home to a massive harbor and highly populated city. If Doggerland was a country of its own instead of belonging to one of the existing European nations, it would probably be a powerful nation comparable to the UK or Germany. But other than that, it's impossible to guess how this country would have impacted the history of Europe and the world as a whole. Doggerland should remind us of the potential impacts of a changing climate and the dangers many of us will face as the sea levels continue to rise. I'm not saying this is a good parallel for our modern times as we see the northern ice caps disappearing due to man-made emissions, but actually I am. That's exactly what this is. If we continue to warm the climate, we could very well end up like those early inhabitants of Doggerland, forced to move to higher ground until there's nowhere left to go, and then a mega tsunami kills us all anyway. What I'm saying is we should look out for mega tsunamis more, and take this as a lesson that we must adapt to Earth, not the other way around. So maybe we should carpool and recycle and not eat so much beef. Thanks for watching, I hope you enjoyed this, and look for more videos from me in the future. And please leave a comment telling me how to properly pronounce Dogger, and maybe give some more ideas about what Doggerland would be like today. Thanks!